announcement, and it's not very major, but I think you've heard it before, but in case you weren't here to hear it. Normally, well, let me first make this one. I've already told Slim, because we were talking about it earlier. He's the first one here. Normally, at 5:45, when this class is over, I usually straighten things up in my office, gather the stuff to go home, and leave about 6 o'clock. Tonight, I've got to sit at the help desk, so I will be here at least until 7 o'clock. So if you do need any office hours or office time or stuff, I won't be in my office. I'll be out in the lobby type area at the admissions desk, sitting at the help desk. So if you do need anything you're wanting to make up or anything else, just come there. I can get it for you. So far, from what I hear from other instructors, nobody's coming by the help desk. This is for summer term, and so we're just sitting there. So come on by. Did they?
That's what it looked like.
Huh. Now, I saw one person from registrar's office when I was.
Parking lot is fairly empty.
What?
Parking lot is fairly empty.
Yeah. I have a feeling a lot of people are doing late lunches and probably long late lunches. In fact, I'm guessing that's where some of the automotive guys are. Is that right? Or you think they went home? Okay. But they were over there. I assume maybe they didn't go over there. But I saw them, like, when I was coming back, I saw Trevor and Camp, passing by one way. So I know they were here. And that was after the ceremony, so they didn't go home immediately anyway.
I didn't know we had so many instructors. Y'all were coming in.
Yeah. Yeah. Well, that's both campuses. And I was right in a group that had a bunch of nursing instructors, so that's a big program, so they have that. I was around a lot of automotive students, and shoot, y'all have quite a few instructors there. Each program has, what, 2, and then you have another 1 or 2?
The Ford one, they sat way up at the very top, like they didn't make it in time.
Okay. Yeah, are there 2 Ford instructors? I know there's at least 2, and maybe more than 2 GM instructors.
Yeah, there's 2.
Okay, and then Toyota, at least 1 or 2? Yeah. Yeah. So I know there's, so a lot of departments have, quite a few, and that's career tech, it's a lot. Computer science, business, there's quite a few majors here. Okay, but what I was going to say, so I'm here till 7 o'clock tonight, so if you need office hours, I'll be out there, not in my office. And then tomorrow, I'm normally on the Birmingham campus, 7:45 to 1, not tomorrow. I've got an infusion tomorrow, so I will be at the Kirkland Clinic probably by 7:45. My infusion is supposed to start at 8, and usually it goes till about 4 or 4:30. So I'm not going to go back to campus after that. I'm not even supposed to be driving very far after that. So just because of the Benadryl and the Tylenol and stuff. Okay, any questions on anything we have done so far? Now, let's go another quick review on what we're going to do today. If you remember last time, or if you've listened to it, we skipped heat flow. So we could do the latent heat and that kind of stuff. The chapter is put together rather strangely. So we're going to go back and do heat flow, and then we'll skip the part on phase change, energy, heat, and molecular theory, and phase change, and then come back in and pick up the last part, which is evaporation and condensation. So we'll do heat flow, and then skip what we've already covered and do evaporation and condensation, and then we'll do thermodynamics, and that will end the chapter. Okay? So we'll finish that relatively quickly today. Not super quickly, but not that much more to cover. Then we'll start Chapter 6. Chapter 6 is electricity and magnetism, which I know all of you have had in some form or another, especially the electricity part. How much of the magnetism part you probably know already, but it's going to be there. So we're going to start that. But the trouble is in the usually 2.5 hours to finish this chapter and start that. We're not going to get far enough to have a lab today, I don't think. And with only 4 people, probably would be not the best idea to have a lab. Hopefully some more will be coming in. So we'll probably go straight through today on presenting the material. So next time we'll do the first electricity lab. Then Thursday we'll have the second. Back off again. Since we're going to finish chapter 4 today, the last 30 minutes of class on Tuesday will be the chapter 4 test. The 2 hours before that will be the first electricity lab. By 2 hours into Tuesday, we'll have enough covered for the first lab in electricity. Yeah. It's going to be circuits. Old hat to you, okay? And then the second electricity lab will be Thursday, and that will be Ohm's Law. Again, old hat to most of you. And then the following Tuesday, we'll have the lab on electricity and magnetism, electromagnetism, and that's probably going to be pretty familiar to you all too. And then hopefully by then we'll be into chapter 8, and then hopefully we'll be far enough along that the following Thursday, hopefully we'll have a chance to do that lab. But if not, I think we still have class that Tuesday, the following Tuesday, and then have our final on Thursday. Is that how it goes? It's been a long time since I looked at the college calendar, so I don't know for sure. But it looks like we're going to have time to get all the labs in, even though we won't get one today. Okay? Any questions? All right, then picking up where we left off last time, depending on what kind of and here's the man of the hour. Congratulations. Okay, Alfred's here. All right. If you remember last time in chapter 4, we did specific heat and then we jumped over to do latent heat. So we could do the lab that we did on Thursday. We skipped heat flow, so that's what we're going to pick up today. So by the way, we have enough for a basketball team now. Okay. So we only had room enough for a bridge table before. Okay. So, all right. Any questions before we get started? Okay, picking up at heat flow, and if you have your text, that's somewhere around page 96 or so. Now, just the term heat flow, that harkens back, and I think I've hit on this a couple of times, to the concept that somehow heat was an element, that it actually flowed, like there was some substance or material to it. There's not, but for, centuries, I would say millennia, people thought heat was an element, okay? They just didn't know how to isolate it. Of course they can't. It's not. It's a form of energy or energy transfer. But we still use terms as if it's a material flowing. And it's not a bad term either because heat does move. It transfers. So we're going to look at these 3 mechanisms of heat transfer, and these are the mechanisms due to the temperature difference. Okay? Remember, there's 2 types of heat transfer. One changes temperature. The other changes phase. And that was the latent heat that we jumped over and did last time. So this is still talking about the temperature difference, where we would be using specific heat if we were using it. So these 3 mechanisms for heat transfer are conduction, convection, and radiation. We'll go over those each with their own set of slides. Okay, the natural flow is always from high temperature regions to cooler temperature regions. So when your dad said, shut the door, you're letting the cool out, in the summertime, that wasn't quite true. You're letting the heat in because heat always flows from high temperature regions to cooler ones. Okay? That's the natural flow. Okay? So,
Does that mean that cool temperature don't flow?
No, it gets pushed around by the... Yeah, exactly right. So it does flow, but it's always heat is going from high temperature to low temperature. Okay? So let's start with conduction. How would you describe or define conduction? conducting heat. Well, that's heat flowing through matter. Okay? I think I told you the little experiment we did when we were talking about specific heat. It was a physics meeting we went to, and they had the plate and the Bunsen burner under it, and the holes drilled in it, and the pegs, and you held onto the pegs. Well, what was happening, the Bunsen burner was heating the plate, and the plate was fairly thick and had holes drilled in it, and the heat was being conducted through the plate, through the peg, and then onto your hand. Okay, that's conduction. Heat flowing, again, there's that concept of flowing. It's not really anything there to flow, but flowing through material or matter. Now, what's the mechanism for that? We know heat doesn't flow. There's no substance in heat. Okay? Well, this is sort of a description of it. If you put the Bunsen burner or the candle, whatever it might be, here under one end of a metal pipe, then your thermometer stuck here in contact with the pipe is going to go up first. This one's going to go up a little, that a little bit. This one, I'm not even sure the heat's reached there yet. That may be room temperature there. Heat seems to be moving down the metal pipe. Why? Well, if you remember that temperature is a measure of what? Said it on several slides so far. Temperature is a measure of the average kinetic energy of the molecules of that substance. The average kinetic energy of the, okay, so when you heat a material, what does it do? The molecules move faster. They bounce harder, okay? The hotter atoms collide with the cooler ones, transferring some of their energy. The energy isn't flowing, it's the atoms are exchanging the energy and moving them down the thing. It's sort of like, this is a dumb example, but the communication game, have you ever played that one? You stand around in a circle and someone whispers a sentence or something in somebody's ear and they tell the next person, next person, next person. When it comes back to the original, nowhere close. Yes, exactly, okay. Also called the rumor mill, okay. That's exactly the type thing. Well, that's the same thing here. The atoms start moving, and remember, they're in a metal. They don't have to be metal, but this is a metal, or in a solid crystal structure. Remember, in the crystal structure, all those atoms can do is vibrate. They can't rotate, they can't translate, they just vibrate. Well, they vibrate faster and harder, and bounce into each other harder, and they exchange of momentum, just like the balls on the track, remember? They do that within the structure, and these bounce fastest, and they bounce into these, bounce into those, bounce into those, so the heat gets transferred down there. It's the energy transfer. That's what heat is. Direct physical contact is required, okay? Conduction does not happen in a vacuum. It can't happen in a vacuum. It has to be a material there to do it. It's heat flowing through metals, okay? I mean materials, not matter, okay? Now, we have good conductors and we have lousy conductors. One name for poor conductors are insulators, okay? Styrofoam's a pretty good insulator. Wool is okay. Air really is a really good insulator, okay? Except the air moves too freely, okay? But if you have still air, that's a good insulator. That, frankly, is why wool is a good insulator. Because wool, if you think about it, wool shirt, these are mostly wool pants. Pretty hot sitting there, but these are pretty thin, so it's not too bad. But wool, like that wool overcoat you might have, if you think about the wool fibers are trapping air in them. So it's really the air being the good insulator. Because that air doesn't move, it's trapped between the fibers. And that's why a flannel shirt, which is cotton, is usually warmer than, this is maybe cotton too, but this is a flannel. There's not much airspace here. And that's why your good old thermal underwear, it has those little pockets of air and stuff in them. Good insulator. Okay, air, still air is a pretty good insulator. Urethane foam, a really good insulator. Rock wool, Fiberglass, that puffy stuff, you see it in the picture in the text. The fiberglass is a pretty good insulator, but what's more, all that dead air that's trapped in between the fibers of the fiberglass, that's the good insulator. Okay? Poor conductors are good insulators. Okay? Now, what's happening here's a picture of what I was trying to show with my wiggling hands, is here. These atoms move very rapidly, and they make these move, and make those move, and make those move. Now, the movement hasn't gotten to these down here yet, or very little, but that's how heat flows or is conducted through a material. Okay? Now, all right. I knew he had been in the building. Okay. Threat or promise? Never mind. We won't do that. Okay. All right. It's a lot like, y'all remember the old cowboy and Indian movies, okay? Sometimes it was the Indians doing it, but sometimes it was the cowboys and robbers movie. If they wanted to know when the train was coming, they put the ear on the track. And why is that? Because the energy, the sound, went through the metal much better than it went through air. Okay? So they could hear it a long way further than they could. I'm not even sure. Butch Cassidy and Sundance Kid may have done that. I can't remember. It's been too long since I saw that movie. Y'all are too young to remember that movie. A classic. I mean, Paul Newman and Robert Redford, one of the best movies ever made, I think. Okay? You don't remember it? Never heard of it. Y'all even know who Paul Newman was, probably. Made salad dressing. That's all he knows. Yeah. Okay. If you can rent that one, it is a good movie. Okay. They made another movie together later, which I thought was even better, The Sting. Incredible movie. Okay. But that's beside the point. Putting your ear on the track, you can hear it because the metal conducts the heat much better than the air did. Okay? Now, and let's talk about that. Metal conducts heat better than most materials. Certainly better than wood, even though that's solid too. Better than fiberglass. Well, we already mentioned that, but ceramics, those are really poor conductors usually. And there's a reason for that. Let's see if we're going to hit on that. I think we probably will. Yeah. Here are some sample conductivities. And if you want a few more, table 4.3 in your text, somewhere around page 97, has even more. But the very best conductor, these are relative conductivities here, is silver, a metal. Okay? Now, don't look at that one. Look at the one in your book. Right behind silver is copper. Very close to silver. And nothing else is really all that close to it. The next best in your book is aluminum. And next best after that finally is iron. But look at that. That's almost 1/9 the conductivity of silver. And then lead, then concrete, then glass, then tile, brick, water, a pretty poor conductor. Okay? Now you might say, oh, wait. You get in water and you can lose heat really easily. Well, yeah, losing heat and conducting heat is not quite the same thing. We'll talk about that in a minute too. What's that?
It's a good conductor for electricity.
What? Water? Actually, pure water is not. But water is such a fantastic solvent that you never have pure water unless you buy absolutely, what do they call it? Not what you buy to drink. If you go and purchase distilled, deionized water, that's a lousy conductor. Because water is such a good solvent, it, just about anything it touches is going to pick up materials from it. And a lot of those materials are ionic, like a sodium ion and a chloride ion. Salt is a great conductor. So if you have anything dissolved in the water, just about all water has something dissolved in it, that's what makes a good conductor, because those ions move freely in the water and they conduct like crazy. So pure water, though, is not a good conductor, but the ions within the water would conduct better. Electricity, anyway. Okay. Wood, not a good conductor. Cotton, even worse. Now, we're talking heat here. Okay. Okay. Cotton, that would be your flannel shirt. Okay. Styrofoam, glass, wool, air, vacuum. Okay. Vacuum is zero conduction. Okay. Now, let's just see the next slide. No. Why is that the case? Why are your metals the best conductors and then the other things usually pretty poor, and you get down here and they're lousy? They're good insulators. Say again? Okay. Okay. You're pretty close. If you're counting on the atoms vibrating to pass that down the line, atoms are sort of big, especially metal atoms, and they boom, 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 boom. They're pretty lousy conductors. Okay? What metals have that most materials don't have are something called free electrons. Now, if you've got chapter 8 in your book, or those books that do have the table in the back, the periodic table, the atoms up here usually bond by what we call covalent bonding or ionic bonding. Okay? The metals are usually in here. In fact, these blues are your metals, purplish or whatever you want to call it. They're the metals. And what the metals have, and we'll talk about this in the chemistry chapter, they have some other electrons that start filling these intermediate shells here. You feel the S shell here, the P shell here, the D shell, and on like this. Well, those electrons in metals are called free electrons. They don't really belong to this atom or that atom. They belong to the whole matrix of atoms, and they're free to move. Electrons are tiny, almost no mass. They have mass, but very small. The electrons are what are doing this. If these were atoms, that would be going down the line. Very slow conduction. Ceramics, terrible conductors of heat and for electricity as well, because those are big, bulky molecules that don't vibrate much at all. But the electrons are very free to vibrate, and they transmit really well. And silver is one of the best to conduct. Copper just behind silver, okay? Aluminum just behind copper, but not all that close. And then iron and your other metals are usually somewhere in there too. Your nonmetals, pretty bad conductors until you get down to the really good insulators. Okay? That's conduction. Mostly through material, matter. Mostly through solid matter. Because think about it. That liquids, those molecules are close together, but look, they just move past each other really freely, so how is this one going to really impact that one much at all? Not a lot. And air, or gases, those are free molecules. They don't collide much at all. They do, and they transmit some, but not the way, that's not conduction for either liquids generally or solids, or liquids or gases. And by the way, liquids, gases, the combination of those two are called fluids. So when you talk about fluid flow, you're talking about either liquids or gases. Solids are not fluids. Liquids and gases, both are fluids. All right, so there was conduction. Okay? Now, before we move on, there's a pretty good little blurb, Science and Society, at the top of page 97 or wherever it is in your book. Require insulation. Okay? And it's probably talking about something here, but on the rare winters when we actually have snows in the area, it's really pretty interesting to look around your neighborhood and maybe look at your own house and look and see how long the snow stays on your ceiling, on your roof. If it stays quite a while, you probably have pretty good insulation in your house. But if it's melting before all the other neighbors, you know what? You probably would save yourself some money in the long run to have some insulation put in the attic. And here's something else you'll notice all sorts of things. The north side is going to keep the snow on it longer than the south side. That's mostly because the sun is going to hit it. Okay? Oh, he did decide to show up. Okay. All right. But one thing you can note, and one of the earlier either editions of this book or the previous book I used for physics had a real neat picture in it. You can see this house, little bungalow type house, and it was in the wintertime in some area that had, lots of snow, and the roof had quite a bit of snow on it. But you can see the family room off at one end of the house, and you can see the driveway used to go there. Well, what had they done? They had closed in the garage and made it the family room and put the garage on the other side or built a separate garage or done something. But you looked at the house and the family room, the snow was, you could tell, was melting pretty quickly. What had they forgotten to do? Yes, because most of the time you don't insulate the ceiling in a garage, but you do in your house, especially in the northern climate. But when they went to add on the garage, they probably did it in the spring or fall, not add it on, but, close it in. They forgot to go up there and put insulation in. So, why is this family room so cold? Or why is this so hot? And that's the reason.
Same thing, they got a porch.
Yeah.
And they turn
Close
it
it.
into a room, close it in.
Yeah.
You're not using a solid floor. They just put carpet on top of the deck and
Yeah.
wonder why that room's so hot.
Yeah, or cold, depending on what time of year it is. In fact, I'm embarrassed to say we did that in our house. It was a previous builder had built on the back of the house a den and a porch, screen porch, okay? And the den he insulated well, but the screen porch, of course, he didn't because it was open. And we kept the screen porch for a while, but all the pollen goes right through the screen. I mean, not even stopping. Mark's here. We're beginning to fill up, sort of. So, yeah, so it made it was just a screen porch, and it was just so hard to keep clean because, like I said, the pollen came in, the dust came in, the dog came in. I mean, so we finally just said, let's close it in. And we had a really good builder, and my wife had gotten the materials and the colors and all like that. And it dawned on me one day when he had already started the construction of it. I said, we never talked about insulation, but I think John will think to do that. But let me get home early today and remind him of that. Well, I got home early, and he was just finishing putting the ceiling in. I went, John, did you put any insulation up there? He said, oh, we didn't talk about that. I didn't look to see if there's any behind it. I said, this is a screen porch. He said, you're right, probably didn't have any. But he had just put up this pretty intricate ceiling, and we didn't want to pay for him to take it down, insulate, and put it back up. So to this day, I can see when we do have frost on the roof, I can see, look out the upstairs window in the back of the house, there are snow. The family room side hangs on there. This one starts melting pretty quickly. So in the really coldest weather and in the hottest weather, we just close that off. It was a screen porch, so we could close it off anyway. So we do, but it was embarrassing that I didn't think to tell them to be sure to put insulation. What's that? No, it's actually on the slide. The rafters were just above it. Well, I was going to have them just had plywood on it, you know, so I was going to have them take the plywood off and put fat insulation between the rafters, and then if you wanted to, put the plywood back up there. I knew it would cost a little more, but it was one day late thinking of it, and it still bothers me that we didn't do that. Yeah, but yeah, that supposedly they can, but you see, it's a brick wall on this side. That was the original house, so there's no place to get there. Out here, you'd have to blow it uphill, which I don't think would blow too well. And what my wife had chosen for the ceiling was, y'all know the old pressed tin that they have in some of the older buildings, you know, yeah. Well, she got pressed aluminum that made it look like pressed tin, and that came in sheets 4, and he had to affix those, you know, individually up there with false beams in between. I mean, he did a great job, but the trouble is he forgot to put the insulation, and we hadn't specified it, and it made me sick, but too late. So no, there's not much place that we have that we could do that, and I could live to see talk about it. My wife would kill me. Yeah, so no, never mind. All right, second form of heat flow or heat transfer is that of convection, and this is energy transferred through the bulk motion of hot material. And let me just give you the hint on this one. Conduction, mostly solids. That's atom to atom, electron to electron transfer. Convection is mostly fluids. What two types of material make up a fluid?
Air and liquid.
Second?
Air and liquid.
Yes, gases and liquids, absolutely. Okay? So this is transferred through the bulk motion of hot materials. And this is why air seems like it might be it's not conducting well, it's convecting well. That's why water convects. It doesn't really conduct well. Heat we're talking about. Because what happens, and again, think of what's happening microscopically, on the microscopic scale. The atoms now, the molecules now speed up, average kinetic energy of the molecules. That's what temperature is. As you raise the temperature, add more heat. They're moving more energetically, so they bounce further apart, right? As they bounce further apart, they become less dense because they're not as close together. And if it's less dense, where do they go? Up, and the more dense comes in. It's sometimes called the chimney effect. It's exactly why the chimney takes the smoke out of the house, because that hot gas with the smoke in it moves up the chimney, and cold air from the room, moves that way. Okay, that's why the upstairs apartment's always hotter, or the upstairs floor is always hotter than the downstairs. Because heat moves up, heat rises. Okay, energy transferred through the bulk motion of the hot material. Space heaters, that's exactly what they do. If it's just there, now if it's got a fan, the fan's doing something. But if it's just a strip heater, say, and in fact, when my parents built the house that my sister is in now, it's the one I grew up in from 6th grade through until my parents died, actually. They had these strip baseboard heaters, they call them, electric heaters, and all they did, they had resistive coils in them, and the air came in the bottom, heated, and went out the top, and you had the, that's all. No fans, nothing. That was an example of convection. Also, if you remember the old schools, and I don't know if y'all ever went to any, that had the radiators.
Yeah.
Okay, that's all that happened. That just was hot water or steam going through the radiators. But nothing was blowing it but the metal would get hot. They had all the veins, and it's sort of like a radiator in a car too. The veins there in between, and the cool air moved up, and warm air moved out. Okay, warm air moved up, cool air moved underneath. I can remember both my grandmother and great aunt had what they called the floor furnace. Somewhere down in what we would call a crawl space, or it could have been a basement, but both of them were crawl spaces. They had the furnace down there, and there was a grate on the top. Boy, that room was hot. You know, the one that was above it. In my great aunt's house, that was in the hallway, so all the rooms got a little bit of that. My grandmother's, it was in the.
Remember the one used to be in the wall?
No, what do you mean that?
It was made like the floor kind, but it was, I guess, like a, you know how a wall mirror is?
Yeah.
It was in the wall and it stuck out ahead louvers.
Yeah.
All the way
Okay.
down.
Okay. All righty. I know the junior high that I went to was a fairly new school, and they had, the old grammar school that I had gone to had the radiators. You could tell when the steam came through, bang, 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 I mean, the pipes would make noise and stuff like that. And you could tell it was getting hot. The junior high I went to, they actually had the pipes in the floor. Okay, and then the tile on top of that, and it warmed the floor. And it came up. Of course, if you ever had a leak, you have to tear up the floor to get to it. But it still was a pretty good system. Okay? But those were examples of convection. Natural convection is the mechanism, and the mechanism is hot air rises, just like we were saying, the chimney effect. And here's a picture of the old radiator in the corner of the room. Used to have them by the windows because the windows were the coldest area of the room. So right by the window, the cool air comes under, heats, you know, in all those spaces you have between there, and the warm air goes up, and you have convective flow. The whole room will get pretty warm, especially if that's over near the windows for the coldest part. You're fine. Of course, if you're sitting right by the radiator, you could probably get way too hot, but you know, most of the room would be pretty good. No fans required. Convection takes care of it all. That's what made it so neat about having it on the floor. You didn't even have that there. Everybody got about the same heat. Okay. Now, why is that? This is their best example of this. So let's take an example of 2 cubes of air. You haven't turned on anything here. Any cube of air you get in the room is going to have about the same number of molecules, right? Now, these are artificial cubes, but just think of it. Imagine that was an imaginary cube of air. Same number of molecules, same temperature, right? Now, if this cooler air coming in here, one of these cubes, this one, goes under the radiator and it warms up, the molecules move, bounce into each other harder, you know, they're moving faster so they get further apart. Now, the same number of molecules are now taking a bigger area. And if you think about it, that's the same mass that you had before. It's just a bigger area. But if you shrink this down and say, no, I want a cube that big, but the molecules are further apart, then this is denser. So that's, the cooler air stays down here, the warmer air goes up here, and that gives you the flow. Sort of a weird example, but it kind of works. Okay. What's that? I didn't know. I know in standard ovens, like when we redid our kitchen, my wife she's a really good cook. I'll blame it on her. But she wanted a convection oven, not a microwave. It's a normal electric oven, but she wanted convection because supposedly it cooks a lot better, and it does. It allows for the flow. I didn't know microwaves did convection too. Do they?
Yeah, convection.
Microwave. Okay.
If you look in a microwave, it's all metal on the inside.
Oh.
More than likely, I got one. You can use it as a microwave or.
Okay.
Convection.
Oh, okay. I got it. Okay, it's either or. Okay. I didn't know microwaves could go. Okay, I got what you're talking about now. We don't have one of those. Our microwave is just a microwave. Okay. Remember the example we gave of the wind at the beach? We were talking about convection then. If the soil temperatures are high because soil has a low specific heat, the water temperature are a little bit cooler because water has such a high specific heat, the hot air rises and the cool air off the ocean off the Gulf of Mexico come in, and that's why you get that good, strong wind in, and it's cooler. It feels cooler, and it is cooler because it's coming in off the ocean. But, not that any of you would stay up late at night, but if you did, you might find that the wind at some point starts going the other way. Okay? But you might not realize. Never mind. It's not that funny, is it? Okay. But it does, and that's why the sailors used to leave port at night, because the wind would be blowing them out of port, not into port.
You can catch it flying longer at night than on the
What's that? Yeah.
on the beach.
Yeah, oh yeah, because you're going against the wind during the day. Now, usually early morning and late evening, though, when you're walking on the beach, I know that's what you're doing late evening, and early morning too, I'm sure you're out there walking the beach. It's so still. It's so nice because there's hardly any wind at all, and the temperature is just about perfect. Okay.
Sure, we have to wait until you
What's that? Yeah, maybe I don't go into the water then. I just walk along the beach. The sun's not so hot then. I'm not much of a beach person. Okay. The third type, radiation. Now, radiant energy is the energy associated with the electromagnetic waves. Okay? And guess what? Oh, they didn't mention this. Go back to convection. You think convection is going to work in a vacuum? No, because there's no material in a vacuum. So how can you have bulk motion of hot material? You can't. Convection depends. Conduction depends on material being present. Convection depends. Radiation does not. It can operate in a vacuum. Not only can it, it works best in a vacuum because there's nothing to get in its way. This is how the energy from the sun makes it to Earth or anywhere else in the solar system. Because basically space is a vacuum. There's maybe a few particles every now and then, but it's basically a vacuum. So radiation actually works best in a vacuum. Now, all objects both emit and absorb radiation. In fact, sometimes they call them black boxes or black body, activity. My wife gripes at me in the summertime. She said, "Get away, you're radiating," because I'm just about always hot. So everybody and all objects do. If you, I can remember when we were kids. My mom was a nurse, so she was always worried about us getting colds and things. And if we did have a cold, we weren't allowed to go out and play, but we could, on the warmest part of the day in the wintertime, go out to the south side of the house where the sun was shining down and stuff, and usually the wind was blocked and we could play there. Of course, that was the dullest, most nothing going on that side of the house. For some reason, where we lived, it wasn't. And we had to stay there if we had a cold. It made you want to get well better, faster. But the thing is, you'll feel the heat radiating off the bricks, radiating off the block. We have a rock wall I built, I think I told you about, in our backyard. And if you get close to that in the wintertime, you can feel the heat radiating back off of that. So all objects both emit and absorb radiation. Now, the temperature determines three parts of this. The emission rate, that's the rate at which the heat is coming off of it. The intensity of the emitted, now they're talking about light here, but they should be talking about heat. And also the type of radiation given off. Now, really what they've done here is jumped from any old material to very hot materials, okay? For instance, those little heaters, that all they are coils, maybe with a reflector behind it, okay? That is radiant energy. There's no fan, but it's a little bit more than conduction because you're getting that. So as those coils heat up, the hotter they get, the more heat is emitted. The intensity of the emitted light, originally there's no light at all, but as they heat up, they get redder and redder, hotter and hotter, and could go maybe up to a whitish type color. That's really hot. It's probably going to burn out pretty. and also the type of radiation given off. By the time you get here, you're talking about a star or something. And that's how they measure stars. They look at the radiation given off. The coldest stars are your red stars. Believe it or not, red is a cold type of heat. Those are dying stars. They're on their way out. They're sometimes very big stars, and they're often called red giants, but they're on their way out. They have pretty much lived most of their life, and they're on the way out. The medium type stars are the yellowish. Our good old sun is a medium star. Average size, average height, heat, just about average on everything, okay? The very hottest stars are your blue or white to bluish white stars. And if you think about the flames, have you seen these on the Bunsen burners? Now there's a good yellow flame, that's a middle of the road type heat, okay? But have you seen most Bunsen burners? Blue. That's a much hotter flame than a yellow flame, and the yellow flame is even hotter than a red flame. When you're burning wood in the fireplace, most of that is red to orange, okay? Not a lot of heat. If you were burning propane, well, that would be pretty dangerous, but that would be probably blue flame. So that's what they're talking, whoops, too far, okay? The type of radiation given off, okay? Temperature is determined by the balance between the rates of emission and absorption. If something's emitting rapidly and not getting much in, then that will determine how much temperature, the heat of that. If it's absorbing, a big deal, and emitting just a little. Now, the example they give here, I'm surprised this author does it, but global warming. Okay. This morning, when I drove in, it was still around 61, 62. Pleasant feeling, but a little on the nippy side. I actually, when I first left the house, I turned on the heater for a little bit because it was just a little cool, okay? And because it was cool, I just came into the building. I didn't think about cracking my windows, okay? When I went out about 9:15 to drive over to the other campus, it was hot in there. Much hotter than the outside. Why? Have y'all ever noticed this? Sure, you have. What's that? Why was it hotter than it was outside?
Because that hot air can escape.
What?
The heat can escape.
Okay, how did it get in though?
You see the effect of the cool space.
Ah, okay. Say again? Okay, you're absolutely right. When the light comes in, generally this light that comes in is not heat necessarily. It is the visible spectrum of light. But when it comes through the glass, it loses just a little bit of energy. Now, let's back up a minute and talk about the spectrum. Okay? What's coming off of the sun is really high energy radiation. Gamma radiation. I mean, stuff that kills you. I mean, it fries you. Okay? You're dead within a few minutes of being exposed to it, or maybe a few hours or a day or two, but the radiation actually destroys tissue. Okay? Why are we not dead? Because we got an atmosphere around us. And the atmosphere we have around us, thank you very much, blocks just about all of the deadly radiation. Out there in space, it's deadly. I mean, it really is. Totally deadly. Okay? Because that radiation, there's nothing to block it. So our atmosphere blocks most of that harmful radiation. Now, the gamma radiation, the X radiation, I mean, X-rays, we use them, when someone has dental work done or hurt foot or leg or something, broken bone or something, they use X-ray, but they use just a little bit and for a very short amount of time. You're not going to die from that, okay? But if you ever notice those X-ray technicians, before, even in the dentist office, before they turn it on, what do? They leave the room. They get behind the window and watch you from in there. Have you ever wondered why they do that?
So then we get exposed to radiation.
Yes, they're around it all the time, and if they stayed in there, they would soon get more radiation than their body can handle, and they probably are going to develop some cancers or things like that. So they get behind, why can they get behind that glass? What kind of glass is that? Leaded glass, you're absolutely right. It has lead in the glass. It's really thick too. The radiation basically doesn't penetrate that. Well, okay. So let's go back. The gamma radiation, the X radiation, cosmic radiation, that's all the harmful, deadly stuff up here. Then you get to a band they call the ultraviolet radiation. Okay? Any of you familiar with that? Say again? You buy your sunglasses that are UV rated. Okay? If they're not UV rated, don't buy them. Don't waste your time. You're just trying to look cool. That's all it's going to do for you. Get them so they do block, because some of that ultraviolet radiation does get through our atmosphere. How can you tell?
Sunburn.
You get sunburns, exactly. That ultraviolet radiation is what, and you the redhead, you have freckles and stuff, you are going to burn probably worse and faster than the rest of us. But my mom's family had a lot of redheaded, so I can, I've got some, I have to watch it too. I put on sunblock. In fact, today I think I forgot, but I put on sunblock every day because right there is a place that's precancerous. What's that? That does. That's why I always wear a hat. In fact, when I went into the gym over at the other campus, I put on my mortar board just to give me that. I didn't want to carry my hat in and that. So I didn't have my robe on, but I had my mortar board. Okay. So, you have that ultraviolet radiation. Now, not just sunburn, but actually that is radiation burn. You're sunburned on your skin, and that's why when you're out in the sun much, tan. That's cool, right? You get a good suntan? No, it's not very cool. What you're doing, you're forcing your body has melatonin, isn't it? Or some word like that. Keratin, not melatonin, what helps you sleep. Keratin. And your body will push that to the surface as much as it can. And actually, the redheads have freckles that have concentrations of it, but you don't have enough in the rest of your skin. That's why you burn so easily. Some of you folks who have a bit more than the rest of us, you're lucky. You tend not to get skin cancers at the rate that we do. I have. You can still get sunburn, and you still can get skin cancer. Okay, but you got more. I know it. See, he has more keratin.
You go out to the beach where the air is clear and the sun is bright. The sun reflecting up on you.
Okay, but you see, you don't have quite as much of keratin as he does. That's part of it. And the thing is, it will get you.
There might be sunburn.
Generally, you know it if you're sunburned, don't you? Okay, I know it when I'm sunburned. Okay.
I can be out in the sun all day.
Yeah, and that's because your body is handling it because you got more keratin in your skin pigments than we do. Okay. Now, so that's the ultraviolet radiation. Now, not only does that burn your skin, if it repeatedly burns your skin, I've had one skin cancer removed here, and this is precancerous here. I have to watch. I put on sunblock every day. Remember to, winter and summer, just to keep the ultraviolet radiation from causing any more damage. But I've also had cataract removed from this eye. If you live long enough, you're going to have a cataract. Okay. Some people might have to be 100 or so before you get them, but it would certainly help if they're UV protected, UV sunglasses. But see, when I was young, I grew up on a farm. I was out in the sun all the time. I didn't wear sunglasses because I'd sweat so bad and I couldn't see through them anyway, so I didn't do it, and sure enough, I got a cataract. Now, I've got a small one in this eye, but it's not big enough for them to remove yet. But you're going to get them. If you hang around long enough, you're going to get them. And have you seen these people who were the sun worshipers when they were young, what are they when they're old? Prunes. Yes, exactly. Their skin is all wrinkled and gnarly and stuff, yeah, because you have damaged tissue, big time. Yeah. Right. Okay. So that's the ultraviolet radiation. Then from there you get to visible spectrum: violet, blue, indigo, violet, indigo, blue, green, yellow, orange, and red. That's the visible spectrum. That's the white light coming in. I don't see any of those colors of that light coming in. Where are they? Get you a prism and put it here, and you would see exactly those colors, right? That's the visible spectrum. And then below that, at the red, the longest wavelength, the lowest energy, you get what they call infrared. And infrared basically is heat. Okay? So what happens? This happens in our atmosphere. It happens in this glass. The light, the visible light comes through, and as it comes through, it loses a little bit of energy. And as it loses energy, the wavelength lengthens. So you do get some infrared coming in, but that doesn't have enough energy to go back out. So that's why your car, or a greenhouse, or someone sitting by the window here will get hot because the infrared gets in but can't get out. So when Camp said it traps it inside, that's why it traps it, because the infrared radiation doesn't have enough energy to make its way back out. Well, guess what? That's happening in our atmosphere too. We are far enough from the sun, we should be a frozen planet. Not super bad frozen, but you see, our atmosphere lets the visible light in, but as it comes in, like I said, radiation moves most effectively through a vacuum, but when it goes through a material, it loses some energy. And as it loses energy, that visible light coming in lengthens the wavelength and becomes heat. So that's what makes us nice and comfortable, that we can support life and live here, but that heat can't always escape. Now, what is it about our atmosphere that keeps it in? The most effective gases at retaining the heat are those with carbon. Now, there are some others. Methane, carbon dioxide, and I think there are some that don't have carbon in it, but those are the ones that do. So that's why they think as we increase our carbon dioxide level by burning more fuels, whether it's cars, coal plants, burning wood, burning down the tropical rainforest, doing all this stuff, that you're putting more and more carbon into the air. The Industrial Revolution, carbon dioxide level, not going up much, but a little bit. So that little bit may be just enough to raise the temperature fractions of a degree, but every fraction of a degree, maybe a little more ice melt, and we could be getting into problems. Okay? I know global warming isn't a popular thing. There's a lot of controversy on it. The Earth has been through cycles of warming and cooling and warming and cooling. We call them the ice ages, when the cooling part. It's natural. However, the curve we're on now is steeper. I mean, those things usually took probably tens of thousands, if not hundreds of thousands of years to move through those phases. It seems like we're in a bit steeper curve now than we were before. And that's where the arguments come. No, this is just a natural phenomenon. Nothing we do is going to make a dab of difference. It'll make a little difference, but not enough to make any difference. Well, if you look, we have had set record highs globally. I'm not just saying U.S. The global temperature, we haven't been measuring global temperatures for more than a few generations. I mean, we just haven't had the technology. But since we have been doing it, I don't know, 70 years, 170 years, whatever it's been, we're having more record highs more frequently now than we used to. I mean, you can't take any 1 year, that's too short a time period. But think about this winter. I can only remember 2 or 3 weeks that we were really, really cold. You know?
I'm trying to think about that.
Yeah.
I can't think of it. Probably got bugs from last year still. That's what I was saying. Mosquitoes gonna be ridiculous this year.
Yeah. But then my brother said, where do they have the worst mosquitoes? Minnesota. Okay. What do they, those are just hardier mosquitoes there. I mean, you know, they winter over, and when they come out, they're hungry. Okay, but no. Yeah. But that's what global warming's all about.
They said that for real.
What?
Minnesota have the worst mosquitoes.
Well, they do have pretty bad mosquitoes. You see, Minnesota is the land of 1,000 lakes, so there's lots of places for mosquitoes to breed. Yeah, so it's. But actually, even Alaska, they say when you do have the thaw, the mosquitoes come out big time. So
There's a lot of water sitting there.
yeah, there's a lot of water around too. But the thing is, there'll always be mosquitoes. You know, it's like gnats. I mean, I don't know where they go, but they're always going to be there. Okay, but that's the principle behind global warming. Exactly. That's what I've heard too. They'll go anywhere that's aggravating in my time. Yeah.
Let me ask you this.
Yeah.
I ask all my teachers this.
Uh-oh.
And I don't understand. When I'm in my car,
Right.
every time I go to the ATM in the car, it shocks me. I ain't talking like a little small shock like when I touch it. It shocks the mess out of me.
What? Oh, shock you. Oh.
Yeah, we have too much money in the bank. What's causing it to do that?
Okay. What is it that shocks you?
When I touch the numbers on the ATM, it never fails. Or
And you're in the car.
when I'm in the car, or if I touch, like I went to McDonald's the other day. When me and the girl touched, man, what's shocked like that?
Okay. What kind of?
Yeah, they close. But it ain't
Okay, that
never.
was exactly my question.
It just started doing that though. I had the car for a while. It just started doing it.
Huh. Is there anything you changed, like floor mats or?
I ain't changed nothing. It's shocking to mess up. When I go to the ATM, I ain't talking about no small shop. I'm talking about it shocks. Like,
I'm wondering if you have a very small electrical leak somewhere in your system.
it might be it.
So what do you do at the service station? You can't, like, anything.
No, it's just happening on the ATM.
Okay. See, what I was thinking was scooting across your seat a little bit. That's static electricity. We're going to talk about that later. And if, say, the seat is probably a synthetic cloth, it's probably not, something that's really durable. And if you wear more cottons or maybe silks or something else, you may be doing it. And have you changed your wardrobe? I mean, in between when it wasn't doing it and now.
Probably so. Normally I'd be going to work, but now that I'm not working, I do wear more like jogging pants.
Okay, that could
like
be it.
cough t-shirts and stuff
You know
like
what they
that.
used to do a long time ago for that? People had these little strips hanging out their car and rub the ground. They ain't gonna look good if
Here's the other thing you can do. Take your key or something like a key, reach out and touch first.
Okay.
And that way and actually sometimes you'll actually see the spark happen once you discharge. I'm thinking when I worked for radon research.
What if you touch the person that got next to you?
It never happens until I go to the ATM or something.
Well,
Be like, hey baby.
I thought it may be in my door or something, because I have my own door,
Yeah.
or you know what I'm saying, maybe the switch is
well, that's why I was wondering if maybe you have a little leak somewhere in your electrical system. That would be the other possibility.
I'm talking about it's not a shot it's not like a small shot, like when you shock somebody.
That's why I think maybe it is you have some sort of electrical leak. But here's the thing that I was basing on. When I was doing radon research for Southern Research Institute in Birmingham, we would go down to Florida. There was around Lakeland and Bartow and some of those areas in Florida. They did a lot of phosphate mining, and phosphate brings up small traces of uranium that later becomes radon, and radon can get into people's houses. So we were doing studies there, how to mitigate that type of stuff. Well, we would stay at, fairly cheap motels. We didn't have big budgets and stuff. And they almost always had this sort of cheap carpet there. And if the motel was built with metal, though, every time you reach for that, scooting your feet across the thing, that cheap carpet, and you reach for the doorknob, it shot. So I found out what I had to do was get the key out first. That back when they had keys, not parts, but even a part key would do it, and do this. And sometimes that's why I say literally you can see the spark.
I think I will, because I can hear it when it's shot.
Yes.
And look, I can hear it, and then when I touch the touch screen, because it's going to ask you, which account you want, it shot me again. So you ought to see me at the ATM now. I've been just like this the whole time, just nervous, trying to thump the numbers or whatever, to go hit it and get it.
But when you walk up to an ATM, it doesn't.
So I walk up to an ATM, and then if I'm in my wife's truck, which it don't have anything. I could be just as long as I'm in this car right there, my car got nothing. It does it every time.
Well, either you have a very small electrical leak, and like you say, it's transmitting through you, because you don't feel it because you're at the same potential it is, but the machine is not, so you haven't changed the potential. You're trying to get in the next chapter already, okay? So, but that's what's happening. Or you got static electricity. Yeah. And it would be interesting if it's. What's that?
Static electricity ain't real low, unless the temperature, air temperature is cold, right?
Well, actually, you're right, but it's not the coldness, it's the dryness of the air. Okay, so that's what the next thing I was going to ask. Have you ever done it when it's raining? Or you get up and go into the thing?
You know what? I've been trying to get money in place when I go to the grocery store and they ask cash back.
Yeah.
I just start going to the ATM card.
So if there's a lot of
less than the air conditioner when they try to.
Okay, yeah, you're absolutely right. If that was my next question. Is it worse when the AC's on, or the heater also dries out the air? Either air conditioner or heater does.
A glass of water with you.
Yeah. So that's what I was going to say. If it's raining, do you notice it then?
I pay attention.
You don't. Yeah, you don't do it.
I'm trying to get money from them.
Okay.
Remember the Adams family? The one you
Yeah.
put a light bulb in the car and make call?
Uncle Festus.
Yeah.
Okay.
Hey,
Y'all are young people. Y'all don't know.
that metal and stuff that you and still, it started to come back on.
Get in the circus, man.
All right. Okay. Y'all are getting into chapter 6 already. Okay. We already did heat, energy, heat, and molecular theory. We did it last time. So we'll skip these slides. So if you weren't here, go back, listen to YouTube, and watch this. So we covered quite a bit there. Here is where we stopped, though, I think, wasn't it? We did this slide, and we did that. Okay? And we did, this. So I think this is where we begin here. So this, if you're in the book, jump over to page 102 approximately. Okay, we did that example 4.7 in the book last time. We wanted to do that before we did the lab. So now we're going to talk about evaporation and condensation. By the way, this is yin and yang, okay? Like melting and freezing. Melting is when you're adding heat, freezing is when you're taking heat away. Evaporation, when you're adding heat, condensation, when you're taking heat away. What's happening here, the individual molecules can change phase at any time. All that depends on what the average kinetic what's the kinetic energy of that molecule, okay? So you might say to yourself, well, how can it evaporate if it's at room temperature? And you know it can. If you set a pan of water out there on the desk and it never got anywhere close to boiling, and you set it out there long enough, it's going to evaporate. Well, that's because the individual molecules can change phase at any time. Now, this doesn't usually happen melting and freezing. That has to be at a certain temperature, but when it's changing from liquid to gas or gas to liquid, mostly gas, liquid to gas, what is happening, the molecules in the liquid are all kinds of different velocities because they're bumping into each other. Someone slow down, someone speed up. And if some of those get up to a high enough velocity, then they can escape that cohesive bond that they have with the other molecules. And that's what evaporation is. And especially if the air is very dry, okay? Because then there's not enough moisture in the air, and the air is trying to suck the molecules away, okay? When it's very damp, then it's less likely for them to escape. So evaporation is when the energy required to overcome the phase cohesion, that's what we're talking about, the the molecules tend to stick together, but not in a fixed lattice. So they just tend to stay near each other. But if it picks up enough energy that it escapes, the energy required to overcome that phase cohesion, then that's what evaporation is. The higher energy molecules near the surface can then escape, and that leaves you some low energy. So here's a picture. Here we have a bunch of water molecules in the beaker of water here, and some of these are at 5, let's say, average kinetic energy. They're not giving units, say in kilojoules, okay? Some are at 10 kilojoules, some are at 15 kilojoules, and some are at 25 kilojoules, okay? Now, which would be and by the way, if they had drawn this properly, this lower energy are probably going to be near the bottom, the medium energy in the middle, and the higher energy near the surface. Why? Heat rises. Convection, exactly. The higher energy molecules are going to be a little further apart. The slower moving ones, colder ones, are going to be closer together. So if they had drawn that right, that would be the case. So these 25s up here, if they get near the surface, and especially if there's a deficit of water molecules in the air is very dry, you've been in air conditioning or heating, either one, and the air is relatively dry, then these tend to escape. Okay? Well, what happens? Okay? The average kinetic energy with these, if you added up all these kinetic energies, 115, divide by 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 molecules, then your average was 11.5. Okay? So this would have the temperature that would be corresponding to 11.5 kinetic energy, kilojoules, whatever that happens to be. Okay? But those two escape. Those are your highest energy. So now we have this. We only have 8 molecules. But the 225s escape, and you lost 50. This was 115 before. Now it's down to 65. Okay? 65 divided by 8 is 8.1. This is lower average kinetic energy than this, because you only lost, you lost a fifth of your molecules, but you did, but they were the high energy ones, so your temperature is dropped. Now, I've seen a picture in one of the other books that I've used, and these work mostly out west, where the air is usually pretty dry. The people carried their water around in a canvas bladder, you might say, okay? And because it was always evaporating slowly from that, when they drank their water tasted pretty cool, because the average kinetic energy. Because some water was always evaporating, it was higher energy level, so the water. Okay, no, it wasn't closed. Remember, it was a canvas type container, so water could evaporate slowly. It didn't wick away, but it evaporated away, and that kept the container cooler. It's sort of like what your radiator does on your car, okay? The molecules of air that are touching that, they take the heat away, and so that drops the temperature of the water that's still in the radiator. Okay, that's what's happening. You don't want to lose the radiator water, but you transmit the energy through the veins in your radiator, and it takes it away. So it's not actually the molecules leaving, but the heat leaves, but the same type of thing. And that's what's happening. And that's, by the way, well, I'm going to get into this now, but maybe it's a good let's wait a little bit. We'll come back to that.
We were in a room with a humidifier. You had an open container of water. Would that water slow down from evaporating?
Okay, humidifier or dehumidifier? Humidifier. If you had a humidifier in the room, and that doesn't happen too much here in the southeast. It does some, because we're usually pretty moist. But out west, especially in the desert, they have humidifiers in their air conditioning system because it's so stinking dry that people, really have problems, skin cracking, and stuff like this. So they humidify all the time there. Yeah, it would slow down the rate of evaporation. A lot of people who use wood stoves, they'll put a pan of water on top of the wood stove just to add moisture to the air because that's going to dry it out. And some people like to then put things like orange peelings in there or pine or something else to give the air a nice smell too. It has nothing to do with the other, but they have the water there anyway, so they do that. But yeah, so that's what's happening. If you're evaporating water, that water is cooler than the room temperature would be. Okay. The higher energy molecules near the surface can then escape. Condensation goes the other way. If this was a cold glass of water, had ice in it and stuff, you may have noticed it in the lab. You set it down on the table there, soon the whole container is wet on the outside. Where's that coming through? Is it leaking through the glass somehow there? No, it's in the air. The kinetic energy cools as you get close to that glass, and then the water comes out of that. So that's condensation. Molecules near the surface lose the kinetic energy, the liquid molecules emerge back in. Now, maybe this isn't a bad time to do it. Why does a fan work to cool you? Is it dropping the temperature of the room?
Taking the heat off your body.
Okay, very good. Your body is a radiator. Okay, I like using it being on the side point. Okay, but what is happening there? We're at 98.6. The room's at 71. Now, if we didn't go back to the earlier slide, if we weren't emitting radiation, we'd be getting hotter and hotter and hotter. But we are emitting radiation. Now, what is our mechanism for cooling off? Exactly. Why does that work?
Why does it work?
Why does sweat work?
The heat will build up in your body.
Okay.
It'll be released somewhere.
Okay, but
Water
sweat
on things
isn't
cool
heat.
down.
Say again?
The water on things cool down.
Okay, sort of, close. Here's why.
When you make it wet and you blow air across it, makes it feel colder than what it really is.
What you're doing is blowing away these hot molecules. Okay? And that's exactly what you're doing. You see, your body has what they call there's a name for it. Goodness, I can't think of it. A boundary layer. Okay? Your skin and your tissue is a certain temperature, and the air right next to your body is pretty close to that. And generally, the more hair you got, you tend to hold that, trap it in a little bit more so. Okay? So you have this boundary layer. So what the air is doing when it blows across you, what Camp said, is blowing that hot air, the boundary layer, away. But what it's doing even more than that, you're always sweating. I'm sorry, you're probably perspiring. I sweat, but you probably perspire. Okay. What it's doing is always coming out, okay, and then the air, these warmer molecules leave, and that's what's cooling you off.
You say you always sweat?
Generally, yeah, unless it's freezing outside, you're not sweating much then. But, when I lived in Nebraska, which was really, really cold in the wintertime, if it wasn't icy roads, I rode a bicycle because I was a grad student. I didn't have much money and I was real cheap. So I rode a bike into work. I didn't live too far from work. And, when it was really, really cold outside, as long as there wasn't ice on the road, if I rode the bike in, I'd be sweating by the time I got to school. Of course, I had on bundles of clothes and, But yeah, you typically are always sweating. Your body is always trying to cool, and what cools you is the evaporation of the sweat. You don't realize it, but you don't realize you see there's moisture there, but it is. It's leaving just about as soon as it comes out because it's close to 98.6 temperature, and the room is 70 degrees, so it's evaporating away pretty quickly.
You come in here and it feels cold here because it's sweating.
Okay, yeah, and then it's evaporating too fast, and you really feel cool. Yeah, that's exactly how that's how your body regulates temperature. We had an English instructor who used to be, y'all had Miss Duncan? You probably haven't. Oh, you have, okay.
I got it now.
You got her now.
Oh, yeah.
Okay. The English instructor before her was Dr. Frankie Hitchcock, and she had some sort of a condition that she couldn't sweat. So she would get so hot. She was a redhead too. She would almost pass out. If the AC wasn't working, she would get blood red, beet red, and stuff, and really struggle. So they had to keep her office in her classroom. People wore jackets in the summertime in her classroom because she could not sweat. She had to have room temperature very, very cold. And actually in the wintertime, she'd sometimes sleep out on the screen porch, just she hardly ever heated the house because when we had meetings over there, we didn't have meetings at her house in the wintertime, because it was just too cold. But yeah, some people have that condition. You can't sweat, you overheat. Now, why is it that what problems do we have here in the summertime? We really don't get as hot as the deserts in New Mexico and Texas. Say again?
Their humidity is different.
Well, what difference does that make?
The humidity, the moisture in the air is what
Okay.
hurts us.
Why? How does it hurt
It
you?
makes it feel like it's hotter than what it is.
Why?
I don't know. This is
Because
what
you,
science
well,
tells
your
us.
sweat can evaporate.
Yeah, okay, because if it's very humid, those sweat molecules can't escape because the air is already close to saturated. There's nowhere for them to go. So you can actually have a heat stroke just because the humidity is too high. And they watch that football games now. They didn't used to. In the early season, they'll sometimes call special timeouts for the teams to go over and cool off. Because if you can't sweat, you're sweating, but if you can't evaporate the sweat, you can have a heat stroke from that. Okay. So yeah, it's pretty serious situations.
Or people like get hydrated when they go to the west.
Yeah.
Or these stroke from cocaine.
Yeah, and you can dehydrate without knowing it because you're losing that moisture all the time. And yeah, you're absolutely right. Okay. Now, let's move, and this is the last section in the text. It's thermodynamics, 4.5. And by the way, there's a couple of other pretty good illustrations. Remember the one about the beakers of water? That's in the text. But they also show a bottle of Listerine. Listerine, by the way, you can tell by the taste, it has a fair amount of alcohol in it, which actually vaporizes easier than water does. You have that bottle sealed up there, and you see droplets on the inside because the Listerine is evaporated and then cooled on the outside of the bottle. That's not very good. But in the old days, probably none of you remember this. Yeah, exactly, because the alcohol has evaporated and then condensed on the inside of the glass. We were way ahead of our time when I was growing up. My mom used solar-powered clothes dryer. Yeah, it's a clothesline. Okay, okay.
You try to
And
get all technical with it.
what's that?
You try to get all scientific with it.
A clothesline, exactly. Yeah, yeah.
Did
And,
did you rotate, or did you just have the long line?
Say that
Did
again.
yours have the fancy upside down tree that rotated, or did you have the line?
No, we had lines, like 3 poles and 3
Were they
lines
on the
between
plane
each.
system? You didn't have to walk around.
We walked around.
I Hey, some people put them on rollers that way.
That's the folks that live in little high rises.
Yeah, but yeah, and in Europe they hang them between the buildings and run them back and forth, you know. Yeah. But actually, at the farmhouse in Georgia that we built, it has pretty high ceilings, 10 feet, in some places maybe even 12. It's a new house, but it's old. And so my wife found this out. It was developed in Europe, and there's a rack that you can roll up and down, and in the laundry room, if you wanted to dry something, hang your towels across the rack, and I mean it's like this, and roll it up, and up there the temperature is always warmer, and just let it dry up there rather than having to use the clothes dryer, and it really works well. And you don't even see it because it's above eye level, So she's sort of strange too, I guess. Oh, I didn't say that, did I? Okay. And by the way, okay, I can't hear it, but maybe I shouldn't. I don't know.
As I'm sending the link to this YouTube video to your wife, hour 26. That's where he says it.
Watch this video. We'll send the link to your wife.
Oh, I see. You're going to help her do that. Okay. She's not going to. Look, she has to listen to me enough. She's not going to sit down and listen to another 4 hours. I promise you.
That's what we'll put in the hour 26.
Oh, I see. Hour 20.
Okay.
You think we're in here 26 hours? No, it's only 4.
No, hour 26.
Oh.
Hour 26.
I see. Gotcha. Okay. He's too clever by half.
26 hours.
Okay.
They've been married long enough, she probably already know everything.
Yeah. We were talking the other night. We were at our godson's birthday party last Sunday night, and Karen was saying how she never can remember the punchlines of jokes. I said, yeah, I can just tell the same joke over and over, and she forgets the punchline all the time, so match made in heaven. Never mind. Okay. And she loves to cook, and I love to eat. It's a match made in heaven. Okay. This is this little strange concepts applied here. They say, why is it called a pop can? This isn't the reason, but what would have happened if you had dropped your Pepsi bottle before you opened it? Yes, exactly. And why? Because, and even when you first open it, you always hear, especially if it's got any fizz to it, because it's been pressurized, the carbon dioxide in that. Yes?
I got a question. All right, speaking of that, why is it every time, like, a drink like that can sit there?
Yeah.
Or there, it doesn't taste normal. But my God, once you shake it and drop it one time, it is flat. Oh, it's awful. One of the tastes, one of the
Okay, it's flat after you
shake
shake
it.
it.
You shook up a Coke and drink it. I mean, it's nasty.
Okay, because when you open it after then, more of the gas comes out and there's less fizz in it.
Yeah, but if you don't, like, you just sit
If
and
it's
drop
brand
it.
new, you drop it, and then you open it, and it's going to be flat. Tastes flat.
Okay.
That's not that problem. Drink water. Water don't go flat.
Right, exactly. Well, the thing is, when you open it, whether you hear it or not, if you've shaken it, and it's even if it's sat there, some of that has escaped when you open it. It does, and you've lost a lot of the fizz. That just the irritation. And I think also if it gets hot, I'm not sure on this, but I think if it gets hot, too hot, and then even if you cool it later, open it, it may be a little on the flat side too. Yeah, because the thing, and you may not notice it, but more of it spews out when you first open it. Okay, maybe enough of that. All right, let's move to thermodynamics. And again, thermo means heat or temperature, and dynamic is changing. So what this is a study of heat and its relationship to mechanical and other forms of energy as that heat is being transferred or changed from one form to another, dynamic. Thermodynamic analysis includes three pieces. The whole system, okay, the surroundings, the system that you're studying, the surroundings of that system, and then the internal energy, which, see, I wish this were a separate topic. Really, this doesn't belong here. You got the system and you got the surroundings. Remember in the lab we did last time, we were trying to measure temperatures that glass It was warm water to begin with. We put ice in it, cooled after it melted. We tried to measure the temperature there. But most of the systems came out with a heat loss because you had uncovered the system, put the thermometer in to measure it, and the room was picking up or losing heat. The glass was losing heat to the room because the room was at 71, the glass, or let's say 20 degrees, and the glass was at 24, 26. It was warmer. The water in the glass or the container was warmer, so you were losing that. So you see, you lost some heat to the surroundings. So you have to study the system and the surroundings. That's everything around it. Now, what you're studying is the internal energy, the total internal potential and kinetic energy of the object in question. We were studying the water, okay? Water that had been iced, you know. Those are what we were studying. And now basically, the kinetic energy, internal kinetic energy, that was the temperature. The potential energy was when it went from ice to liquid. That was the change of potential energy. And we incorporated all that. So your energy conversion, this is how you change energy, okay? Friction, that converts mechanical energy, the energy of motion, to heat. Rub your hands together. They get hot. Your brake pads on the car, when they're pressed together, bring it to a stop, that energy of motion got changed to energy of heat, okay? So friction converts from mechanical energy to heat. Now, believe it or not, those strip heaters, the baseboard heaters, that was using the same thing too. You see the electrical energy moving through the wiring, that the wiring in those strip heaters, of the baseboard heaters, was probably something like, what's that called? That material that they make stovetops. Second? Not the heating element. That's goodness, I know the name of it. I can't think of it. We'll get to it in the next chapter. But what it is, there's more friction resisting the flow of the electrons, and that's why they heat up, because the friction converts the mechanical energy of the electrons into heat. Nitrile. Isn't that a substance they use in heating elements? I believe it is. I think that's what it's called. Okay. Now, what a heat engine does, this is your automobile. This is your internal combustion engine. Okay? Devices that convert heat into mechanical energy. It does the opposite thing of friction. That's why your braking stops the car, and your heat engine is what moves the car. You're converting the heat in the pistons into mechanical energy moving the car. Other applications, heat pumps. What is a heat pump similar to? Heat pump is, yeah. And what else uses a compressor? Air conditioner. A heat pump is just, this is oversimplified, but the whole process of refrigeration, you're blowing the heat somewhere else and blowing the cool where you want it. Just reverse the process, and the heat pump is blowing the heat where you want it, letting the cool dissipate somewhere else. Okay? So it's just basically an air conditioner in reverse. Refrigerator is, reverse of a heat pump. Organisms also are heat generators. And it goes with, like us. I'm 98.6, the room's 71. I'm a heat engine, okay? I'm producing heat. And every organism does. Hurricanes. Good, bad, or indifferent? Is a hurricane a good event, a bad event, or a sort of neutral event?
Hey, you can depend on where you are.
Why do you say that?
If you're in the hurricane, mid-hurricane, you'd be bad.
Yeah, you think it's pretty bad. But how is it good for anybody?
How is it? It ain't good.
Yes, it is, actually. And it takes the heat from the equator and moves it up into the temperate areas. If we didn't have events like hurricanes, We'd be way too hot to support life here and way too cold to support life there. We have to have a mechanism to move the heat from the equatorial region. That's what hurricanes do for us. Now, I never knew that. I was in it was actually a book class at our church, and Jerry Tracy, who's the Channel 13 weatherman, he goes to our church, and there was a big group there, and somebody was talking about how terrible hurricanes were and why God, allowed hurricanes to happen. Jerry said, well, wait a minute, we didn't have them, we couldn't live here. They moved the heat from the tropic areas to the other. They're basically heat engines, okay? Stars certainly are heat engines. They are producing.
So we have more hurricanes because they hotter longer down there?
Say that one more time.
Is that why we have more hurricanes than usual?
Again, that's a real cyclic thing. There were a few years ago, remember when the year that we had Katrina? Yeah. They name hurricanes with a letter of the alphabet. The year we had Katrina, a little bit later that same year, they had Rita over in Texas. That's up to R's. They got through the entire alphabet and started doing A, B, B, C, C. We had way more that year than I think any year on record since they've been naming them. Then we've had some years, I don't know if we got past G or H. In fact, this year, what did we get up to? Does anyone remember? I don't either. Okay, we didn't get very far. It seemed like there may have been an Alfred and maybe so. But remember the other year there was a pretty bad one up in the Northeast. If you lived up there and said, what was a bad one? What was its name? Do you remember? Sandy. We were up to the S's in that year. So some years are really bad years and some are not so bad. But I do believe, to answer your question, the frequency and the severity of them will be getting worse. If this global warming thing is really happening, we're going to have more and more of them, I think. So I don't know. We'll see. Right. Well, that's what melting the polar ice cap is doing, but not a good idea. Okay, stars and big heat engines. Now, black holes, boy, no one really understands them at all. Do you know what we mean by black holes? No, don't be thinking anybody parts. We're not talking that. No. Okay, get off of that. Nasty. Okay. We're talking about in space. Okay, yeah, y'all have sick minds. Okay. Okay, actually it has a lot in it. Okay, here's what the deal is. Huh? Okay. Okay. Here's a rough and dirty on it. When the big, massive, no, you're going there again, aren't you? Okay. All right. Okay. When you have a big, massive star that dies, and they die pretty relative to other stars fairly quickly because they burn up so fast, okay? And what happens, they explode, and then they contract. And they go through a couple of those cycles. Those are called supernovas, and then they contract again. When they finally contract that last time, it's so incredibly forceful that matter just gets condensed big time. I mean, big time. And so all the matter that was in the star that didn't escape somewhere is now in a tiny little area. The gravitational effect is so strong that it pulls other stuff into it, including light. Light can't escape. So there's really lots of energy there, but you can't see it because not even light can escape a black hole.
Now, does gravity here have an effect on light?
Actually, Einstein said it did, okay? And it actually bends light ever so slightly. And we did have an event that happened, seems like it was just a couple of summers ago, and people who know this stuff, I don't know it well, there was a supernova somewhere that they watched it, and I think when the light went past maybe the sun or something else, they did see it bend it, okay? And Einstein had predicted that, and of course nobody wanted to argue with Einstein, but no one could prove it or disprove it. when they saw that, that gave evidence that, sure enough, gravity does have that effect. It's a much smaller degree, though. Okay?
Actually, a black hole is really the opposite of a hole, right?
Yeah, exactly. Except the whole stuff is falling into it, and this stuff is falling into it big time. Okay? So we don't know what happens when it's in there. Like I said, no one really understands them. You can't get close enough to study them yet. But every galaxy, and there's billions of galaxies out here. What's the name of our galaxy? The Milky Way. The middle of our Milky Way. Anytime you have a galaxy, there's a black hole in the big. In fact, a pretty big one. And that's what has all the galaxies spinning around it. That gravity effect is keeping all the stars in the Milky Way. And next closest, anyone know what the next closest one is, or at least a good, decent sized one? Andromeda, exactly. It's even a little bit bigger than us, so it has a big black hole in the middle of it. So.
You learn all this on Star Trek. They start naming stuff.
Yes, exactly. Okay. All right. So virtually any system with energy inputs and energy outputs, those are dealing with thermodynamics. Okay? So let's look at least a couple of the laws of thermodynamics. The first one is basically conservation of energy. Okay? What you have here, the components here, are your internal energy, the total internal kinetic and potential energy. You have heat, which usually is an external type thing. You're either producing heat or absorbing heat. And then you have work, and that something is changing energy into doing something with it, and that's work. Okay? Now, it's stated in terms of changes of internal energy. Okay? If you're increasing your internal energy, you're either adding heat, or doing work on the system. If you're decreasing your internal energy, you're either emitting heat, or your system is doing work on the environment. Okay? Or both. Okay? But it's stated in changes of internal energy. And your heat engines are a classic example of that. You're increasing the internal energy, it's doing work on the system, and also producing heat. Right? Where is that heat going? Okay? Through what mechanism? Okay, the exhaust of your car, heat's going out of it. And we've already talked about it. Through the radiator. Heat's going out of that. And through the brake pads when you use those. Or the tires. Feel your tire after you've been on the road for a long time. It's really hot too. Okay? And even the friction of the car on the road. In all cases, you're losing as you increase the internal energy, some of that's going to heat, and some of it's going to work to move the car down the road. Okay? That's a heat engine. Okay. Here, maybe they'll get to it yet. Okay. Here's an example of a heat engine at work, a very simple heat engine. Okay? We start, and they don't show where you start it. You start with a piston full of air. Okay? And then this piston has a cylinder full of air. I said the wrong word. Cylinder full of air with a piston on top. You put a weight on that. Now that weight is, gravity is pulling it downward, so you're compressing the air, right? You're doing work on the system. You're increasing the internal energy of that air, okay? It heats up a little bit, but you've done work on the system. That's the increase in internal energy. Well, then what happens if you put a fire under that? Now those molecules that have been forced together, they're speeding up, they're bouncing into each other, increasing the pressure, and they're pushing the weight up. So now they're doing work on the weight, okay? So the heat is also increasing the internal energy and doing work on the weight. You know it's work because you change its potential energy here, from here to there. Change of position, that's potential energy. So the heat did work on the piston, okay? And that's exactly what's happening inside every internal combustion engine, right? The heat from the combustion of the fuel and the gases in the cylinder That's what's doing work on the system. Okay? First law of thermodynamics. Here's another way of expressing that. You start with a high temperature region. That's where you put either the combustion or you put the flame underneath. And the high level Q that you've added to the system, some of that does work and some of it is wasted heat. This goes out the tailpipe, gets blown away through the radiator or on the tires, on the brake pad, somewhere with the heat engine. This is what you're wanting out. Actually, more heat goes here. The best, most fuel efficient car that you've got, I'm just making a guess here, I doubt it's 25% efficient. Would you say? Have y'all done any studies like that? A lot of them are like 15, 19%. I don't know if any now. You get into some of the hybrids and stuff, and you probably can get that up 40, 50 maybe. I don't know. But usually you got an awful lot of this going down here. Okay. Now, shame on them. First thing they should have done here, and it should have been on the slide here, but it didn't show up. You choose a color for me. Yellow, I think, shows up really well. Okay. Here is your equation for first law of thermodynamics. I do not like the way they express it, but I will. They call it JQ. Okay. I think that's sort of dumb. Minus W is equal to U2 minus U1. Okay? Now, let me explain what this is. The heat is your Q here. Remember that from earlier in the chapter. But usually heat is expressed in calories or BTUs or some of those old units. When you're talking about work and energy, what unit do we usually use? Joules. Okay? So what this is the joule equivalent, changing heat, calories to joules. So they call it JQ. I think that's really dumb. They should have just used heat and said the joule. That means the joule equivalent of heat. That's what that stands for. So, what this is change of internal energy, U2 minus U1. It's always, like it said here, stated in terms of the changes in internal energy. Initial, final. The change of internal energy. Now, if this is positive, that means you've either added heat to the system or you've done work on the system, not by the system. So this is you're actually adding, or some combination of those. Now, if your final is less than your initial, and this is negative, that means you have done work to the system or to the surroundings, or you've emitted heat, okay? Rather than absorbing heat, you've emitted heat, okay? So there's your first law of thermodynamics. There's the equation for it. Change of internal energy, U2 minus U1, is equal to the heat added or lost and work done on the system or by the system. So that's what the signs are determined by. So they give in the book which way they do. So anyway, and then these other illustrations are showing the same thing. Okay, and that's your heat engine model. Okay, now they do another formula there. Let's go and do that one too. Now this is if there is no change of internal energy, if this is indeed zero, so the internal energy has not changed, then we have JQ minus W is equal to 0. Well, let's add W to both sides, and that gives you W is equal to J. And now really what we're going to do is change of heat, Q2 minus Q1. Now what that one is saying, if there's no change of internal energy, that means the change of heat here is going to produce that amount of work. Okay? and this just is the joule equivalent of that. So this is really a delta Q here too. They just didn't list it. This listed. So if you are adding heat to a system, you're either and keeping internal energy the same, then you're able to do work with that system. Okay. So that's if there's no change of internal energy. So that's the second equation they have. That's equation 4.8. All right, now we're ready for, and they don't have any examples with this. We'll have one later, but it's a little on the lame side. But here's the second law of thermodynamics. First law, conservation of energy. The second law has several different ways of expressing it, okay? And these are all equivalent statements, so they don't really sound like it when you first read them. Here's one of the statements. It basically is saying the second law of thermodynamics. The first law says the change of energy, you account for it all. Energy is conserved, okay? The equivalent statements for second law, no process can solely convert a quantity of heat to work. We saw that in our automobile engines, right? You barely get 15%, 20%, maybe 25% out. Most of it is lost. No process can convert a quantity of heat to work. Totally. You can't do it. You can come fairly close, but maybe in some systems, but most systems you don't even get close. Here's another way to express it. Heat never flows spontaneously from a cold object to a hot object, as in refrigeration. Now, to me, that doesn't seem at all equivalent to this, but I know what they're saying here. Here is a really dumb example. Let's say middle of summer here in Alabama, hot and miserable outside, your air conditioning goes on. So tell me, would this be a reasonable thing to do? Not economically, but just reasonable. Open up the refrigerator and the freezer and let the cold come out, and at least that space around there is going to get cool. Okay, so will the temperature in the room decrease? Really? What is that refrigerator doing? If you think about it. Somewhere behind, above, somewhere there is a, you named it earlier, a compressor. Okay? And you're compressing the gas, making that gas heat, and then behind that refrigerator you have a coil, a lot like a radiator, right? And that's where the heat is being dissipated. And then you're letting that gas that was compressed, heated, lose the heat, then you let that expand again. That's what produces cooling, right? That process of compressing and dissipating the heat, that's in the same room as the refrigerator. You're not pumping that outside, are you? That's in your kitchen too. Your kitchen actually gets warm. Okay, if you had the coils outside, you got an air conditioner. I mean, that's basically what it is. It's not a refrigerator anymore. It's an air conditioner. Because every refrigerator I know, the coils are in the back of it. Or maybe sometimes underneath. In the old days, they used to have it on top. Y'all remember those? The compressor sat on top of the refrigerator? Not that old. Okay. Okay. You're making fun of my age, or I can tell that. I remember your name. Okay. Okay. So. Oh, you got it right. Okay. Never mind. Okay. So heat never flows spontaneously from cold to hot. It doesn't happen. You're having to remove the heat in order to make it cool. Okay. And if you're in the same room where that's happening, you're actually increasing the temperature. Believe it or not, you are. Because what are you doing? Electricity is running that compressor, and it's blowing out. You're actually heating the room. Not very efficiently, but you are. Okay. Here's the third way of expressing the second law of thermodynamics. Natural processes tend toward greater state of disorder. And that concept is called entropy. I don't know if you've run into that word before, but it's entropy. Now, the classic example of that I think of, y'all all know about a deck of playing cards, right? There's 13 cards in a suit, 4 suits, 52 cards in the deck, right? Not counting the jokers or other things like that. Okay, so let's imagine you open a brand new deck of cards, brand new, and you look at them, and it starts with the ace of spades, the king of spades, the queen, the jack, the 10, down to the deuce, and then the ace of hearts, down, and then the diamonds, and then the clubs. They're all in perfect order. So you take them out of the box in perfect order there and throw them up into the air. And say, catch them on a sheet. And you have people at each corner of the sheet. Now, how many times would it take for you to throw them up in the air and catch them all again, over and over and over, before they get back in the same order again? It's never going to happen. You have many lifetimes, and it never is going to happen. Ever. Everything, natural processes tend to disorder. Remember your room? Does it ever straighten up itself?
No, tell them all they will eventually.
Yeah, and does she ever? She knows entropy, doesn't she? She's watched it grow up. No, I mean she. Okay.
That's true.
Oh no, that's because when you weren't looking, Mom came in there and straightened it
No,
up.
she didn't do that either.
No, she didn't
My mom
either.
did not believe in that.
Okay.
Under the bed, you had a lot of room under the bed.
Oh. The bed got a lot of entropy, and the rest of the room didn't. Okay, I see what you're doing. Nothing ever, everything always, natural processes always tend to a state of disorder. That's just life. You have to add energy to a system to bring order to the system. Always. And you could go into chaos theory and all sorts of stuff. There's interesting things there. That's the second law of thermodynamics. No process can be 100% efficient. Heat never flows spontaneous from cold to hot, and natural processes always tend to disorder. Always. Okay.
So is that basically saying if it's not a process, it's order?
Yeah, if you don't add energy to a system, you don't increase the order. Now, I don't want to get into this because it can open big cans of worms, okay?
Let's not.
Okay. But I'm going to anyway. Okay.
Oh,
This is one of the big arguments against the theory of evolution. Because basically the theory of evolution says that naturally things have gotten more and more ordered into living structures and stuff. And there's arguments on both sides of it, but in a sense, in a big thermodynamic sense, that things tend to go to disorder, not greater order. Now, of course, you've got input of force, but of energy. So we won't go there. So let's not. Okay. Now, there's two reference scales. An object's external energy, that's the energy of global coherent motion. I'm running across the room. I'm not going to run across the room, but if I did, that is my external energy. When I tried to tackle Bill Boyce on the football field when I was a freshman and he was a junior, it was painful, but I was trying to change that was the external energy. The energy of the global coherent motion, that's associated with work. Doing work on the system, or the system doing work on you. Okay. Then you also have the object's internal energy. That's the energy of the microscopic, chaotic, incoherent motion that's associated with heat. Okay? Now, we think about that. We've already mentioned it in the automobile. Okay? You've got some controlled system there that is changing some of that heat to work. Yeah, you can always change some. Some of it's always wasted. Okay? That which is making motion of the car, that's changing the external energy of the car. That's what you want it to do. Okay? The internal energy, that heat that's going out the exhaust, lost. The heat that's going through the radiator, lost. The heat that's created the brake pad to brake pad, lost. Heat, tire on the road, lost. All that is lost heat, incoherent, microscopic, chaotic. You can't retrieve that. Okay? Now, I mentioned the hybrids, and Ford does have a hybrid, right? Pretty good one too, right? Is it diffusion? Yeah, okay. Now, do y'all use regenerative braking? Okay. That is not losing that heat that's lost with the brake pad, not losing that to the environment, but reconverting that to electrical energy that can then be used to drive the car. There, your entropy goes down some. You don't have as much loss to disorder. You're reordering that, your system. Do you ever catch it all? I think not, okay? But you can catch maybe even most of it. I don't know. Okay, so let's look at that first statement. Again, this is sort of conservation of energy. That first statement, let's go back to it again. No process solely converts quantity of heat to work. Okay? We're getting pretty close to the midpoint, so we'll be stopped for a break in just a few minutes. Okay? So, let's state that again. Conservation of energy with heat energy. The input energy equals the output energy. You know that's true. That's first law. Input energy equals output energy. Okay? However, the input energy, say for a heat engine, is the chemical energy stored in the fuel, combusting and becoming heat energy, doing work on the piston, that kind of stuff. Okay? The output energy, some of that's work, some of it's heat. Okay? Wasted heat. But the input energy equals the output energy. It's just that not all the output energy is what you want. Some of it's wasted. So the efficiency of heat energy is the output that you want to happen is the work done. Divided by the input, that would be how efficient you are. You see, you can't count the heat loss, that is useless heat, okay? So the second law, efficiency cannot equal 1. You'll never get all the work out that you put in as energy. You can't do it. Some energy is always degraded, and just about always that degradation is to heat. Just about always.
So if you had an engine that was 100% efficient, it wouldn't be hot.
Yeah, exactly. And can you imagine that? That would be pretty hard to do. Okay? You would have to recapture all that and reuse it somehow. Now, things have gotten much better. Now, this isn't a heat engine, but your furnaces in the houses, when we had, we didn't have to have it done. Someone before us had upgraded the furnace in our home to a more efficient model. The old days, the exhaust pipe leaving that furnace had to be metal, double, shielded metal, because that metal pipe got really, really hot. The exhaust was out. Nowadays, our current one has PVC. Okay? Now, in the old days, that PVC would have melted a long time ago because it would get that hot. That's why it was required to be melted before. But now they recirc the exhaust so many times through that system that when the air is finally exhausted, it's just warm air, not hot air. So they have gotten much more efficient in lots and lots of things, but the efficiency never equals 1. Okay, some energy is always degraded. And that's what hybrids are doing, is using more and more and more of that. Okay? So here basically is this equation. Here is your input energy, and there's your output energy. The input energy is basically your heat or whatever it happens to be. The output is the work that's desirable, and the energy loss that's non-desirable. Okay? Your efficiency is the work, the desirable output, divided by the total input. Now, if this was 100%, you'd have no heat loss. That would be it. E would be 1. Can't get there. Second law says you can't. You always go to some disorder. Okay? That's using another phrase for it. So,
would the formula be incomplete?
what's that?
Wouldn't you have to put plus the heat loss on that bottom?
No. Okay. It's the desirable work coming out compared to the total that went in. If there's any loss, this is not equal to 1. Because you see, see, that would have gone up here. If you could have converted all that and got that to be 1, fantastic. Okay? You can't do it. That's what the second law says. You can't do it. And the closer you can come, the better you are. Okay? Now here's the second statement. Let's go back and look at the second statement again. Heat never flows spontaneously from a cold object to a hot object. Okay? So here's the second statement. This is, again, conservation of energy. This is your heat pump, however. Okay, and what you're doing here is, this is basically refrigeration. You're doing work on the system. Okay? You're compressing the air. That's doing work on the system. Okay? When you compress it, you pull from the low temperature region and move it to the high temperature region. Okay? Now, this is a heat pump, sorry, not refrigeration, it's the reverse of that. Okay? And then you blow this into the space. Okay? That's your heat pump, basically. Okay? Now, the energy arriving in the high temperature region is energy from the low temperature region and the work needed to move it. So upgrading the energy by the heat pump accompanied by a greater degradation of energy elsewhere. Okay? Now that, to me, this slide is one of the poorest ones. That's not making a whole lot of sense except if you think about it this way. Okay? The work that you did in here, this is your input. This is your output then. Okay? You can't get all this out, all of what you put in out, because there is degradation somewhere else. Okay? You're not 100% efficient in raising this. You always have loss. And this illustration is one of the worst ones, but that's basically the second statement of it. And I think this illustration is pretty poor. Okay? But it is true. It's just not very clear. Now the third statement, everything goes to thing. Real processes are what we call irreversible processes. Okay? We'll get to that in a minute, but it's coming up right down there. There's always a measure of disorder. That measure of disorder is entropy. The second law in these terms says the total entropy of the universe, okay, is continuously increasing. Okay, now that's a pretty big picture, okay? I'm not sure I quite buy all that picture, but that's what it's saying. Okay, the total entropy of the universe, that's the disorder in the system. So if the total entropy of the universe is increasing, that means the useful stuff is decreasing because energy is conserved. Natural processes degrade the coherent useful energy, and some of it also always winds up as incoherent non-useful energy. The available energy of the universe is diminishing. That's the useful energy is diminishing. And they say eventually this is going to lead to the heat death of the universe, which I don't know what it means. I mean, it's a really big concept, okay? That may be what's happening in black holes. What goes in, you can't ever get out, okay? How long can that go on? Okay, that's the interesting point. And my older brother really likes to ponder this kind of stuff, and he loses me, about a half hour into it, because maybe sooner if he's been drinking. So I don't know. But anyway, I just said that as a joke. Okay. Now, to see if you were listening. Okay. The direction of natural processes always toward the disorder. I told about the deck of cards. It's never, ever going to arrange itself. In fact, not only will it not ever go back to order, you'll never get them all so they'll be facing the same direction. Every time you do it, there'll be some that are up, some that are down. No way you'll ever get back. Their little example is spilt milk will never unspill back into the glass. Of course it won't, okay? But that's entropy. The third statement of the second law. Okay, that is the last slide in the set, and it seemed like to me they should have at least mentioned the third law of thermodynamics, okay? And we actually hit on it a little bit earlier, okay? Remember when we were talking about absolute zero? Okay? The third law of thermodynamics said absolute zero can be approached but never reached. That basically is the third law. You can get close to it, and they actually claim, now this to me is incredible to say they've gotten within a few billionths of a degree of absolute zero. How do you measure a billionth of a degree anyway? How can they even suspect that? I guess that's it, okay. So, I don't know. I don't know if I even believe a statement like that. But you can approach it, but you'll never reach it. That's the third law. Very theoretical, because the only way you could disprove it was to reach it. No one's done it yet, so who knows. All right, that did end chapter 4, finally. Okay, a good place for a break, too. Do you want to save the last words until after the break, or let me go on and finish chapter 4? Just a couple of things here. There was a nice little blurb, mistakes and misunderstanding, something that makes its own fuel, okay? This is around 106. I don't know if that's the same in yours. It's a little lavender-type block, mistakes and misunderstanding. In other words, perpetual motion machine. No such animal. Can't happen, not if it obeys the second law of thermodynamics. Okay? There is a really interesting blurb about Count Rumford. Now, his name was Benjamin Thompson, not to be confused with William Thomson without a P. He was Lord Kelvin, that the Kelvin system's named after. Count Rumford, Benjamin Thompson, was an engineer who basically first made the observation that led to our understanding that heat is not an element, but heat is just another form of energy. He's the one that came up with it. How he did it was really interesting. He was an engineer, and he was hired to make cannons, I think, for the Germans. Okay, he was somewhere in Germany making cannons for them, and what they did, this is way back, 1700s, early 1800s, and what they would do, they'd have a horse turning a big, going around the circle, pulling a wheel around, turning a big drill, and the drill would be, they did cast iron, in the shape of the barrel, cannon barrel, and then drilled out the hole, And, of course, after a few drills, the bit would be useless. You have to add a new bit, because that was pretty hard stuff. And he noticed all the heat that was being produced. And he thought, how in the world could heat be an element? And it seems like we can just keep producing. So what he was doing, it seems like he was working around Munich or somewhere. And that's really pretty close to the Alps. It's in southern Germany, not too far from the German Alps. And what he did, he took an old barrel that was no good. It was off-center or something, so he could waste this. He took an old bit that was really dull, and he started the poor old horse to do it. And he filled the barrel full of ice-cold water that came out of the Alps. Just glacial water almost, really, really cold water. And started the horse walking around in the circle. And within an hour or so, he had that water boiling. boiling with no loss of material. So heat could not be a material. It could not be an element. It was changing the mechanical energy of the horse to heat energy. He was the first one to illustrate that. People went, oh wow. You know, we've seen this all our lives and didn't realize heat is not an inferior substance in the thing, because he could do it all day long. There was no, he couldn't exhaust the heat that was in the bit or the thing. He couldn't. He could, as long as he kept the horse doing, he could keep the water boiling. Okay? Pretty interesting that he could come up with that. And to me, a little more interesting in it is really who this character was. Notice those years, 1753 to 1814. What happened during his lifetime? Yes, they were, exactly. In fact, he was from upstate New York, I believe it was. No, Massachusetts. Okay? But how did he become a count? He's Count Rumford. We don't have any counts, do we? We barely can count. No, never mind, say again. He did. And you know why? What's that again? Okay. What else happened there? You said we were building our country. What else happened in those years? The War of Independence. And he happened to said, I like England. I don't want. He was, say again? Yeah, he was a royalist. That's exactly what happened.
Drink unsweet tea and lose.
Okay. What they actually did, in fact, there are some, I've read a few accounts that he may have actually had some connection to Benedict Arnold. But anyway, he decided to get out of the country in a hurry. Exactly. So what they did, he went to England. He was a brilliant engineer and a scientist, so England was very happy to get him, and they were so happy to have someone who gave up on the colonies, you know, in this war of insurrection, they would probably consider it. So, they what?
You know what they weren't happy about? Losing.
Yeah, before they lost, though, they rewarded him by making him a count. And he was always a really bright guy, so that's why he was Count Rumford. So he's an interesting character. You can write your paper on him, but guess what? This little blurb in your book cannot be a source. You got to get outside the book to get your source. But it's a really interesting character. There is an example here, so let's go back and get this done before we run out of, I'm sorry, I forgot this. I told you it was coming. Example 4.8. A heat engine operates with 65.0 kilocalories, I think it said, didn't it? Yeah, of heat supplied. What symbol do we use for heat? Q. And if that's supplied, what's that? What do we designate as? That's our input. So let's call it QI. They also call it, in other places, in fact, they call it QH. Let's call it QH, the input. Okay? It exhausts 40 kilocalories of heat. Now guess what that is? It's exhausted. We can't use it. So what was that in our formula? QL. That was the low level. Out. Okay? How much work did the engine do? Any idea? Your total input energy was 65. Your total, the heat loss was 40. Is what? Not atom. Remember the formula? QH is equal to W plus QL. Remember the QL is that we cannot use, the wasted. So guess what W is? And which is that? 25. 25 kilocalories. Now, what's a little bit wrong with that picture? We usually don't measure work in kilocalories. What do we measure work in? Or energy? Joules, exactly. So we need to use that joule equivalent of heat. And what was that? Multiply that by your conversion factor, and you want this in joules, or actually we're going to do kilojoules. So what will we want to go where? What unit? Always put the units in their place. What unit goes where? Between kilocalorie and kilojoules, one's above the line, one's below the line. Okay, kilojoules on top and kilocalories on the bottom. Okay? Now we need to figure out what's that conversion. How many kilojoules per kilocalorie, or how many, you could say joules per calorie. So, yes, that equivalent. And they give it to you here. And I like to use the 4.184. Keep everything in kilo. So it's 4.184. That's it, isn't it? 184, yeah. Kilojoules. Wait. Yeah, but because they're using joules, I'm using kilojoules. No, okay. No, they're saying joules. Notice there. Right. They're going to come up with kilojoules, but the conversion they're using joules. And I'd say going to use 4.184 kilojoules for every 1 kilocalorie. See it? And that way your kilocalories go out, multiply 25 by 4, just something a little over 100. What does it come up being? 105 kilojoules. Now, I have one other question I'm going to ask you on that. What was the efficiency of that heat engine? Okay, this was wasted for you. So your useful output was 25, your input was 65. So take the 25 divided by 65, what do you get? 25 divided by 65. Say again? Yeah, less than 50%. Yeah, I'd say maybe low 40s, maybe. Yeah. Anyone do it?
38.
Second?
38%.
38% efficiency. Boo hiss. Okay. Before we go, and here's a little concepts applied thermodynamics in action. Probably worth a read. See what's happening there. Okay. Nothing, you hear it every chapter, nothing replaces reading the chapter. Please read the chapter. Hopefully you've already read it once. Maybe read it again. We will have the test on Chapter 4 on Tuesday, the last 30 minutes on Tuesday. Okay? The summary here, that hits the high spots, but it's a pretty short summary. You can't get it all in that. Summary of equations, you have 8 equations in this one. That's built a little bit more than normal, so well worth jotting those down and bringing with them on the test. Your key terms, pretty small list there, but you'll see most of them in the summary. But even though they're given alphabetically, they give the pages where they're first defined or described. Applying the concepts, 43 questions, maybe a few fewer than normal, but good questions, multiple choice, probably the best thing to study for the test. They provide the answers. As far as I know, most, if not all, the answers are correct. Questions for thought, 17, that's right at or above normal, so well worth thinking through those. For further analysis, there's 7 of those. That's probably a few more than normal. Well worth thinking through those. And then the parallel exercises, those with the book like this, or the thicker books, you probably do have the Group A answers in the back. Those with the little thin books, you don't, but I can get you the answers if you want them. You can take a picture with your phone. I'll make a copy or whatever. Okay, we're skipping Chapter 5. Wish we had time for it, but we don't. And there's some cool pictures in there. And by the way, anything that's there, you could write a paper on anything in that interests you there too. When we get back from break, we will start Chapter 6. Any questions on 4? Okay, why don't we take a break, try to keep it less than 5 minutes if you can, and when we come back I'll call a roll again, and then we will get going on the last couple of hours. No time for a lab. I mean, we haven't covered enough material for a lab today, so we will move on from here to chapter 6. I'm going to go on and... All right. As I said, we're skipping chapter 5. That was waves and sound, good stuff and really interesting stuff, but just not enough time of the term to get it done too. So we're going to start today with electricity. Actually, the chapter should be electricity and magnetism because we do hit them both, but they are both related. It has always been known that they were, but we do know today they are very intricately related. The core concept here, and if you got your text, you'll see, at least in my book, white print on a yellow background, really hard to read, but this is a little easier. Electric and magnetic fields, now we haven't defined what those are, but we're going to talk about that in the chapter, interact and can produce forces, okay, because of the electric and magnetic fields, whatever those are, okay? So let's look at some of the concepts of electricity. Now, they do a pretty good job of this, but they sort of jump into pretty deep right away. They start with electron theory of charge with an ancient mystery, and it was called the Amber effect, not an Amber Alert, but Amber effect. And what this is, from my understanding, the earliest use of electricity was parlor games. Okay? Now, do y'all know what amber is? Not a person.
Color.
Second?
A color?
A color, okay? Actually, the color is named after the substance that was amber. Does anyone know what the substance of amber
Is that
was?
Like a sap
Yeah.
almost?
A what?
Like a sap?
Yes, very good. It's fossilized tree sap, basically. Fossilized tree sap that has become a mineral, a rock, a hard rock mineral, okay, over time. That was amber. And what they found out is that if you rub a piece of amber on, say, I believe it was fur of some nature, you know, some type of animal fur, and do that, then hold the amber up to somebody, you can shock them. And that was the extent of their understanding of electricity. It was a parlor game. It was a very shocking experience, okay? Like Alfred sliding across his car seat, you know, get to the ATM. That was the Amber effect. And that's all we knew about electricity. Now, next chapter we do is chapter 8. We're going to skip 7 also, but we'll go to chapter 8. And we'll run into this guy again. His name is J.J. Thompson. He identified, now let's back up a little bit more. Remember we said, I think in the last chapter or somewhere before that, no, last chapter, chapter 4, that atom was what we called indivisible. That's what it meant. Smallest particle of an element that you can exist and still be the element. Well, they said the atoms were indivisible. That was the name came from that, from the Greek word for that. Democritus had hypothesized that. But really, you can divide things out of atoms, and one of the things in an atom are these negatively charged electrons. J.J. Thompson identified these. Now, we'll go into more of this in the next chapter, and we'll do some of these same type things here. Now, today, what our understanding is the basic unit of matter, especially with an element, is an atom. Atoms are made up of electrons and nuclei. Okay? So an atom is made up of an electron and a nuclei. Now this is a very accurate picture, but it's a pretty decent one. If this is an atom, okay, The nucleus would be that little spot in the middle. The trouble with it is it's way too big, okay? It would be so small you couldn't see it, so they made it big enough so you could see. The nucleus is that thing in the middle, and what the nucleus is, now they happen to do a helium nucleus, a helium atom. They aren't telling you that, but that's what it is. That nucleus contains 2 protons and 2 neutrons. Now, something about these. Protons are positively charged. Neutrons are neutral. They have no charge. Okay, so think of that as no charge. Positive charge, no charge. Electrons have a negative charge. Okay. Now remember, that spot's way too big. That nucleus is extraordinarily tiny and is sort of in the middle of that. Okay? Charles is back. Okay. Now, something else. The protons and neutrons, the nucleus, has almost the entire mass of that atom. The electrons, their mass is so very tiny, it's negligible compared to that. In fact, an electron mass would be approximately, this is just a guess, about 1/10,000th of the mass of a proton or a neutron. I mean, just incredibly tiny, mass-wise, okay? But all this mass, almost the entire mass of that helium atom, is isolated and concentrated in that very tiny little nucleus. All the mass, almost, in a very extraordinarily tiny nucleus. And the electrons, which have almost no mass at all, and by the way, there's 2 electrons, and this is, again, isn't a very accurate representation, because with just 2 electrons, they'd really be in just this part here, but if that was the right size nucleus, just this little shaded part here would be enormous, probably take up the whole wall here, if not more, okay, if that were the size of the nucleus. This is just a cloud here with 2 electrons in it, just 2. And the mass is almost negligible, extraordinarily tiny. But they're floating around anywhere in that space. So all your mass is concentrated in an extraordinarily tiny little nucleus, so it's really dense, extraordinarily dense, okay? And the electrons have almost no mass at all, and they're taking up the entire volume. And when my older brother came home from Georgia Tech after the first physics class he took there, he said, wow, most of everything is nothing. And what he meant by that is in between these electrons, outside of the nucleus, there's nothing there. I mean, it's as void, more void than outer space. I mean, there's nothing. I mean, these electrons have almost no mass. They're flying around somewhere in there in a huge area. So most of everything is nothing, okay? Because all the mass is in the tiny little nucleus. Well, these are positively charged. These have no charge. The electrons have negative charge. So obviously, the charge doesn't weigh much because they have the same charge, these tiny little electrons, as those big old protons do. So that's what we've got. And of course, this is the second smallest atom that exists. Everything else is much more complicated than this, with many more layers of electrons and much bigger, fatter nuclei. Okay. So we'll hit that again in chapter 8. Stand by. We'll get there one day. Okay. What is this electric charge? Okay. If you have that electron, if you could isolate it and play with it, it's far too tiny, but if you couldn't extract that charge from it. That's intricately a part of that electron. Without the charge, it's not an electron. If it's an electron, it's got to have that charge. Same thing about the proton. The proton's part, the positive charge is part of that proton. You can't take it out and do anything else, okay, make it something else. So the electrons are the negatively charged particle, extraordinarily tiny, but float around freely but stay close. And the protons are positively charged, and they're fixed in that nucleus, that incredibly dense little nucleus you have. Now, there's an interaction there between those charges, negatives and positives, and that's what we call electric force. Like charges attract each other, unlike charges repel each other. Okay? Like charges repel, unlike charges attract. So what keeps that electron floating around the nucleus is the fact that you've got two positive charges in that nucleus which are holding that electron close. Sort of like the Earth flying around the sun. The sun's gravitational force keeps us around it. Okay? The difference is the electron is three-dimensional. We basically go in a two-dimensional disk around the sun. The electron is going in a three-dimensional sphere around. It's not a very well-defined sphere either around the nucleus. Okay, but it's electric force that holds those together. Now, helium will not lose an electron. It's happy as a pig in slop to have two electrons. It's not going to give them up. Okay? It loves them. Let's go one thing larger than that to, say, lithium. It has 3 protons, I think 3 neutrons, and 3 electrons. Well, the 2 inner electrons, the same place they were for helium, but that one other electron is just floating around out there with no close neighbors or anything. It's really likely to lose that. If it were to lose that electron, then does it ever gain a proton? No. That would be a nuclear reaction. We don't like to have those, okay? The only way it can change its charge is to either gain or lose an electron. If it lost that electron, what does it become? Slightly positive. Proton, 3 protons in there. Now it only has 2 electrons, so now the whole atom is not an atom anymore. It's a positively charged ion. Okay, an atom is an atom if it has no charge, no net charge. Same number of electrons as protons. But if it gains or loses an electron, it never gains or loses a proton. If it gains or loses an electron, then it becomes an ion. If it gains an electron, it becomes a negative ion. Loses an electron, it becomes a positive ion. So an ion is a non-zero net charge from either gain or loss of an electron. Okay? Do we have any ions in the room? Where? Okay. A few things may have lost something, but they're not like that. Okay.
I wasn't expecting a follow-up question.
What's that?
So I wasn't expecting a follow-up question.
Okay. Okay, if you had a battery in here, yeah, I bet you there is a battery in my computer and there are probably some ions in there. You're probably right. Well, I can't see it now, but I know you're probably right there. How about any others in the room? You might not see it, but you see the effect of it. These fluorescent tubes, there are ions flying up and down those tubes. That's what's producing the light. Because you have a huge capacitor there called the ballast. Is that what they still call it?
Yep.
Okay, the ballast, and that's a big capacitor, and it creates a concentration of charge, 2 equal concentration of charges, opposite charges, and some electrons fly down the tube to balance the charges. Okay, and that's what we'll talk about that last time. So a flow of electrons, of ions in is called a plasma. Remember we talked about that. So yeah, there's ions in the room. Okay, and they haven't left the building. Okay. So here, this happens to be a lithium atom because it has 3 positive charges there. Now, it only shows the positives. Also in that nucleus, there are neutrons, and yeah, I was guessing, and I was wrong. There are actually 4 neutrons. I said 3, there are 4 neutrons. Doesn't matter, they don't have any charge to them. So there's 3 protons and 4 neutrons packed into that tiny, tiny, tiny little nucleus there, all that mass there, and then you have 2 electrons in that inner shell, and that one little electron floating around the outer shell, all by itself, way out there, real easy for it to lose it. And if it lost it, it would become a positive ion. Okay? So a neutral atom, equal number of protons and neutrons. And electrons. Number of neutrons doesn't matter at all. We'll talk about it in the next chapter. It matters a little bit, but not major. Not charge-wise. Now, so if it lost that lonely little electron flying in its outer shell, now it becomes a positive ion. One electron has been removed. It's no longer neutrally charged. It now has a +1 charge. That's a lithium ion. Okay? Never does it gain or lose a proton, ever. You can't do that. That would be a nuclear reaction. Don't go there. Okay? Now, this next figure, they're just doing it for illustrative purposes, but it never happens. And that's this. A lithium atom doesn't pick up an extra electron. It just doesn't happen. If it did, it would become a negative ion. But it doesn't happen, believe me. Trust me, it doesn't. Now, if they had shown, rather than lithium, fluorine, okay, that's at the other end of the periodic table. Fluorine would have, I should know this, but it's been so long I forget, 9 protons in that nucleus. It would have 10 neutrons in that nucleus. Okay? Now it would have, because it has 9 protons, it would have these 2 inner shell electrons, and then it would have a pair of electrons there, a pair there, a pair there, and only 1 over here. Doesn't matter where the 1 is, but it has 3 paired electrons and 1 unpaired electron. That would be 1, 2, 3, 4, 5, 6, 7, 8, 9. That would be your 9 electrons. Okay? It really doesn't like it that way because it likes to have its outer shell filled. And the outer shell for a fluorine atom is 8. It only has 7. 2, 4, 6, 7. Now, again, this is 2-dimensional. It's really 3-dimensional. So it's not shaped like this, but you get the idea. So what does it like to do? It likes to have a filled outer shell. A filled outer shell would just be the 2. Is it going to lose those 7 electrons? No way. But what might it do? Rip off an electron from somewhere else to get its filled outer shell. Now, it has 9 protons, but 10 electrons. It has a +1 charge. That would be the better illustration. I'm sorry, a -1 charge because it has an extra electron. That would be your better example of a negative ion. Okay? They just did it using the same graphic they had. Lithium never gains an extra electron. Fluorine does all the time. Chlorine does all the time. Iodine does all the time. Bromine does all the time. They are notorious for stealing electrons from somewhere else. Maybe from a lithium.
Now, the atom lost an electron and gained an electron. How do you know that it has done that?
Yeah, it becomes...
By the time you look at it.
Okay. You can't see it anyway. But if you had enough of them, you'd see they were charged. You would have a net positive or negative charge. That's how you tell if it's an ion. If it has a charge. If you put a meter on it and it shows the charge, you know it has ions in it. And you'll know whether they're positive or negative. This is what's happening on the microscopic scale. You'll never see it to see that, but that's what's happening. So that's what an ion is. Either an excess or deficit of electrons. Never an excess or deficit of protons. That can't happen short of a nuclear reaction. And we don't want those to happen. So, yeah.
When I was first taught this, they say current doesn't flow. It's the hole that leaves. That's what flows.
Okay, it's what?
Current doesn't flow. It's the hole in the charge that leaves behind is what flows.
Okay. Okay, I understand. I think exactly what they were indicating by that, and we'll actually get to that a little bit later and do that in the first lab. We will actually be doing that first lab. So that's kind of true, There's actually a better way to express it in terms of fields. That's the best way to do it. But back when I think both of us started, you talked about the excess and the holes, and they flowed in opposite direction. That's what, Okay, we'll get there. Okay. So now let's look at static electricity. Those were the parlor games. Rubbing amber with wool and shocking people.
Going to the ATM.
Okay, going to the ATM. That was electrostatic charge. That's a stationary charge confined to an object. Me walking across the cheap carpet at the hotel and reaching for the doorknob and shocking myself. Okay? That was static charge. My brushing across the cheap carpet either removed electrons from the sole of my shoes to the carpet or from the carpet to the sole of my shoes. I either had an excess or a deficit of electrons. When I reached for the doorknob, it had plenty of free electrons, and they went one way or another. It was too fast, I couldn't see which way, and I didn't care. It just shocked me. Okay, right? Did you notice which way they went? Okay. Yeah, you just knew they went. Okay? So, that's what electrostatic charge is. Static electricity. Static meaning stationary, not moving, fixed, okay? Electrostatic charge, you have extra buildup somewhere, it just is a stationary charge. See, static and stationary come from the same root word. Okay, now what's the charging mechanisms? Rubbing the wool on the amber, that's friction. You're knocking off electrons that tend to be lost, gaining electrons that tend to be hungry for electrons. You can, Charles and I, the Charleses can't do this much, but those who, I think Samuel would probably be the most likely to do it, possibly Trevor too. Have you ever, combed your hair and then reached down and picked up little chips of paper with it, with the comb? What you're doing with that, you're knocking off electrons off of your hair onto the comb, getting it to be negatively charged. The paper is sort of neutral, but it's attracted to it because, friction knocks off electrons. Now, something else you can do, contact with a charged object. Now, this could have been Alfred, if his car was have a little bit of electrical leak somehow there, he was in contact with that and reached out. He became in contact with the charged object, and then he transmitted that. Again, that's static electricity. And another way is polarization. Okay? Now, this is reorientation induced without changing the net charge. Now, let's go back to the comb and the little pieces of paper. Okay? You've combed your hair. You've knocked electrons off of your hair onto the comb so it has excess electrons, negatively charged. You reach it down to this pile of little bitty bits of paper you tore up in little bitty bits, and you reach down and the first one is attracted to the comb. That's because this was negatively charged, this was neutral. But then the next piece wants to pick up too. Well, why is that? Well, this first piece, remember the comb has excess electrons. This has neutral, but because it's excess, the electrons on the paper tend to go the other way because like charges repel each other. So they move to the other end, leaving holes, lack of electrons here, so positively charged here. So this is attracted here. That other end of the piece of paper is negatively charged. It then picks up the next one, and it does that. That's polarization, reorienting the charges. The charges were in the paper, the negatives went down and the positives went up, and so you reoriented that without changing the net charge, but you changed the distribution of the charge, and that's called polarization. You made one end positive charge, the other negative. You made that a polar piece of paper. Okay, and my goodness, looky here. James is here. Good to see you. Okay? All right. Now, let's see if we have some illustration of some of that. Oh, here's the gal combing her hair. Okay? Now, initially, the hair is neutral, same number of positive and negative charges. The comb is neutral, same number of positive and negative charges. Everything's fine. But she starts combing her hair, and the electrons from her hair leave her hair and go to the comb. Okay? And when that happens, the comb becomes negatively charged, the hair becomes positively charged, and all her hair becomes positively charged. And then rather than straightening her hair, it looked pretty good before she started combing, now it starts spreading out because the positive charges are trying to get away from each other. So she just made her hair look worse, okay? Now, what was required for that to happen? Not meaning to say anything about her hygiene or anything. If her hair was a little on the dirty side, maybe oily, or she had hairspray on the side, that's not going to happen. Because the more of that you have, you're not going to move charges around. But if the hair is fairly dry, clean and dry, and the air is fairly dry, low humidity, then this is going to happen. Now, have any of you maybe not had it with combs and hair, but have you had other things that when you I'll give you an example. We have a golden retriever. Y'all know, they're fairly long-haired dogs. And she's one of the white ones. They're called English creams. They're more European than they are American. There's a lot of breeders here in the U.S. now with them too. And she's a mess. And she goes out and lies in the oak flowers and the thing, and comes in just covered with stuff. So before we let her in, I usually brush her out, and she loves being brushed, by the way. But when I'm brushing her, I can feel just all the time because I'm doing exactly that. The brush is polyester or something like that, and her hair is not, and I'm exchanging electrons. I can feel as I'm holding her still, I can feel the little charges. She's probably feeling it too. She may like it. She may get a charge off of it. Yeah.
I think it's there's a fleece blanket
at
night sometimes.
Yeah.
You don't go up and you straighten it out, you can see all the
Yeah, if it's dark, you can see it. Yeah, we have a blanket on the bed. Sometimes you throw it back and you see. If the lights are really dark, you can see that. Exactly. That's static electricity. Because two different materials, probably maybe cotton sheets and fleece blanket, different materials, and they pull away electrons, and then you see them try to get back. Okay. Also, have you ever taken something out of the clothes dryer? Yes, that and clean. Okay? Yes, exactly. Different materials, maybe cotton, underwear, and maybe the wife silk something another, and they're sticking together like crazy. You almost have to pull them apart, and if you're in a dark room there, you can see the arcs and sparks when you pull them apart too. Okay, well, the dryer sheet does, it neutralizes those. It becomes the source of sink for any excess charges, so that you get away from the static. Exactly. It's not neutral, it actually attracts the charges that otherwise would be on the clothes. Okay? Now there is another thing, and it's a slightly, I was going to say this one too. I hate to say this about our house, but it has the good old entropy concept we were talking about. We tend to get cobwebs. Does anyone know what a cobweb is? What's that? Okay, it looks like a spider web. That's why they call it a web, but it really isn't. There was no spider there. What it is, what's on the air handler in there? Before the air reaches the air handler, it goes through a filter, exactly. Trying to pull all the particles out of the air, dust particles. Now, it doesn't get them all, okay? Everywhere there's people and clothing, and there's always dust somewhere. Well, if there's dust particles, those dust particles are incredibly tiny, especially the ones that get past the filter. Filters are pretty good. So if they get past the filters, they're very small. anytime you have a very, very, very small particle, you call that particle a colloid, is the name for it, C-O-L-L-O-I-D. And those colloids, because they're so tiny, someplace there's an edge. And some edge may be slightly positive and some other edge may be slightly negative. It's sort of like they're polarized. They're that small that there's some exposed charge. And when you get this positive touching that negative, and there may be another one touching another, and what you have is a series of dust particles linked together, and that's what makes a cobweb. There wasn't really a spider there. It looks like a spider web, but it's really dust particles. Huh? Oh, she will. Okay, tell her it's just a cobweb. But she's not going to like that either. She'll say, well, you ought to be dusting. Okay, never mind. Okay. You'll never win, by the way. You know that long enough. Okay. Okay. Never win. Okay. And actually, that's held together by static electricity. Okay? Now, all those are examples of static electricity. Okay. And this is showing what I was describing. This is an awfully big piece of paper. You need really tiny little things so it'll pick up. But if this cone has, like we said, a net negative charge, gets close to a little scrap of paper here, it's going to attract the positive charges and repel the negative charges. So this becomes polarized. No net change of charge, but just a change in the distribution or orientation of the charge. Since this edge of the card becomes positive, or strip of paper becomes positive, this edge becomes negative, it'll attract the next piece, and the next piece. And you can have a string, and that's what a cobweb is. A string of those little dust particles forming what looks like a web. Okay. Of course, we don't have dust in our house, so we don't have, you don't believe that, do you? Okay. Now, there is a little concept supply. This is around page 142 of your book. And notice how it begins. This application works best when the humidity is low. Okay? And then you can start trying to do this. I've tried several of these little static electricity exercises, and just about always we're way too humid here. Other parts of the country are when you've got a lot of heating or a lot of air conditioning going on. Maybe you can get the air dry enough, but I've seldom been able to do a very good static electricity demonstration, so I've given up on it. So let's move to electrical conductors and insulators. What's that? Yeah, it does, okay. I just don't have enough air to make it work anymore. No, it's not that funny. Okay. So, you're laughing. Okay, you're going to lose points. Okay. All right. Let's look at electrical conductors and insulators. Okay? What is an electrical conductor? That's when the electrons are free to move throughout the material. And what do you think makes good conductors? Metals. Remember in the last chapter we were talking about those free electrons in metals? That's what makes metals such a good conductor, because they have those free electrons that are not attached to, like lithium and fluorine and stuff. Those electrons belong to that. They don't free to move unless they get ripped off, and then you have static electricity going on, and that would work. Okay, but the added charge dissipates if it's a conductor. If you add a charge to it, it spreads throughout the material almost immediately because it's free to move throughout the material. So metals are good conductors generally. Graphite's a good conductor. It's not a metal. It's a non-metal. It's a certain form of carbon. Now, carbon, if you look at that in the periodic table, it's in column 4A, the top element in column 4A. That means it has 4 electrons around it in the outer shell. The outer shell wants to have 8. So it's not going to gain 4 or lose 4, but boy, it wants to react with something. So it makes for a good conductor. Now, on the other hand, your electrical insulators, that's when the electron motions are restricted, as in helium. Helium's not going to gain or lose electrons, so it's not going to conduct electricity worth anything, okay? They don't list it here because it's a gas, it's fairly rare, so we don't do it. The added charge tends to remain on the object, doesn't get distributed through the object. Glass is usually a pretty good insulator. Wood's a pretty good insulator. Unless, of course, it's green wood with a lot of sap still in it, that may be a good conductor, okay? But wood itself is usually a good insulator. Now, diamond, what is diamond? Okay, more than that, it is a mineral made completely of carbon. But wait a minute, graphite is made completely of carbon. How can you have graphite carbon being a good conductor and diamond carbon being a really great insulator? Huh? No, it's the electron structure, okay? Graphite is a two-dimensional structure, and that leaves electrons free on the outer edge. Whereas diamond is a three-dimensional structure, and all the electrons are tied up with other thing within the three-dimensional structure. So that makes diamond a great insulator, with graphite a good conductor. Now there's some other differences there. They're both the same elements. Carbon is the ingredient in both of these. Now graphite, by the way, is there any graphite in the room? In a pencil. The black part of a pencil lead is graphite. It's smooth, it's slick, it's, in fact, don't you use some graphite grease sometime? Yeah. It's a very good lubricant because it's a two-dimensional structure and it's slick, and this pencil slick. Now, the hardness of this, that comes from graphite, they mix the graphite with kaolinite, which is a clay. And that's what makes the more kaolinite, the harder the lead, the less kaolinite, the softer the lead. So a number 1 pencil, this is a number 2, is going to be a fairly soft lead. It just has less kaolinite. If it's pure graphite, it's just soot, basically, is what you got. Okay, slick. How about diamond? Diamond pretty slick? Diamond is the hardest substance, naturally occurring substance known. Okay? If you have little chips of diamond on a blade, you can cut through anything. It's the hardest substance. On the Mohs hardness scale, number 10, maximum. It is an abrasive, the hardest abrasive you got going. So the same element, carbon, makes for a lubricant or an abrasive. How can that be? You can't. Oh, well, okay, what they do. Remember, diamonds are three-dimensional crystal structures. In that three-dimensional crystal, you have what they call the faces. They call them the cleavage planes. Okay? And if you hit the right tap in the right place, you can break it along the cleavage plane. Because some places atoms are tightly fixed and some places they aren't. And if you hit it right in the right place, and that's how they cut diamonds. They really find those seams where you can cut those faces. They're not really breaking. Impossible almost to break between those, but between the planes you can. So that's how they cut it. What's that? No. There's no material known that you can use to cut a diamond. You just have to hit it in the right place. It's sort of like, you ever split any wood? Yeah. Okay. If you, sweet gum, you ever split any sweet gum wood? You have. A lot of work, I bet. Oh, yeah. Yeah. Because sweet gum is a spiral type wood. So there's no, yeah. But if you get a good oak or hickory, you know, you can put that, if you have a wedge there, you hit it, just pop it. And even with an axe, something like that. It just. Say again?
A lot of people make horse tables out of sweet gum.
Oh, really? I didn't know that.
So if you got a horse that will chew up wood, put it out of sweet gum.
Oh, really? Okay. I don't have horse because I hate burns. Okay. I'm too cheap to own a horse. Okay. Okay. But they're nice animals. Okay. So it's sort of like that. So if you take that piece of hickory and turn it on its side and set up your wedge the same way and smack there, are you going to break that? It will not split that way, no way. Okay, so you have to be along a cleavage plane, and that's what cutting a diamond is. It's finding that the plane where they can't separate. If you're inexperienced, then you don't have a job very long because diamonds are awfully expensive. So the experts don't mess up many. But I bet you when you're learning, you probably mess up some, and if you mess up too many, your apprenticeship is over. You're out of the door. Go find another job. Okay. So yeah, it's very intricate. Yeah, but you can mess them up. So that's why they have such different characteristics from a lubricant to an abrasive. How can you get much different? Yeah. And how did that happen? Well, a lot of pressure and a lot of temperature, you change the crystal structure. That's how that happens. And that's why these are good conductors and those are good insulators. But then you have another class of materials, and this is called a semiconductor. Where do you hear that, where a semiconductor is found? Second? Chips in computers, exactly. In fact, and the earliest ones were silicon dioxide chips, right? Semiconductors. They don't conduct well, but under other conditions, they do conduct well. Semiconductors. They conduct or insulate depending on the circumstances, like charge or voltage or whatever, okay? And computer chips, solar cells, just about anything electronics these days have semiconductors. Now, what is the area around San Jose, California sometimes called? Okay, the earliest semiconductors I said were silicon dioxide. Silicon Valley, exactly. That's where it got its name. That's where Hewlett Packard was, and a lot of the early startups. I think was Intel there. I don't know. Several of them manufacturers were there. That's a high-tech area. Now it's much. What's that? End up where? Oh, okay, yeah. A lot of it has moved overseas, yeah. Okay, now let's get back to the basic charges here. Okay? The unit of charge, okay, now let's go back to the concept we did last chapter. Okay? You have the macro picture, the stuff you see, feel, and stuff like this, and then you have the microscopic picture, what's going on the atomic level. That we're talking about, the atoms and the electrons and the proton, that's super submicroscopic. But let's get back to the big scale, the scale we work with. The unit of charge there is the coulomb. Okay? Now, you talk about a big scale, it's equivalent to the charge of 6.24 times 10 to the 18 electrons. That would be 6,240, 000, 000, 000. I think one more set of 000, that many electrons. I said, oh, well, I don't even think there's a prefix that goes as high as 18. Maybe there is, I don't know if there is. Okay? That's the metric unit for charge. Okay? What's the U.S. customary or British unit for charge? Coulomb. Why? Because electricity didn't really come around as a field of study until after the metric had split off from the British system or whatever system they had in France. So everybody started using metric. So we decided we'll just stick with that. It came across later. In fact, everything electrical, same in our system as it is in the metric system. It's the same. SI system is coulombs, volts, amps. Everybody uses the same thing. So what is the electron charge? That's the fundamental charge. Guess what? You can't get any smaller charge than is on an electron or on a proton. You just can't do it. That's the fundamental unit of charge. Smallest charge seen in nature. The quantity of charge is related to the number of electrons. That many electrons produces 1 coulomb. Okay? We measure things in coulombs. We don't measure in terms of electrons. We can't count that low. Count that small. So here's the formula that says this. Q. Now, in the last chapter, capital Q was, it's been a long time. The last lab, capital Q was? Oh, it was so long ago. 2 hours? Okay. E. You just answered that question not long ago. Well, that was capital Q. Here in this chapter, little q stands for charge. So if you see a little q, that stands for charge. Capital Q from the last chapter stands for heat. Don't get them confused. Completely different. This is measured in coulombs. Heat was measured usually in calories or BTUs, whatever. Okay. So Q is equal to NE, where E is 1 electron charge, that fundamental unit of charge, and N is the number of electrons you have. That would give you the charge that you have in coulombs. Okay? Now, here is then what an electron charge is, that smallest unit of charge. If you have 1 coulomb, we said that was 6.24 times 10 to the 18 electrons. So take this, divide both sides by N, and 1 coulomb divided by N, 6.24 times 10 to the 18 electrons. 1 electron charge would be, if you take this and do it on your calculator. Now, do you know how to enter scientific notation on the calculator? In general, don't do times 10 to the 18. That's a long way to do it. Okay? Most of your calculators will have a key on there that says either EE or EXP. Okay? If you find that key, you put 6.24, then press that key, EE or EXP, and usually you'll see a little block go up, and if you type 18, you've got it. That EE or EXP is your times 10. And then what you enter next is that X bar. Okay? And if you take 1, divide it by 6.24, EE or EXP 18, you're going to get an answer for equal. You get 1.60 times 10 to the minus 19 coulombs per electron. That's a very small number. That would be 0.000, comma 0, you don't put commas here, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 6, or something like that. What's that? 6.24. Let me see your calculator. Now don't do it times.
No, you just hit
Do the EE, and you see those little 2 digits there? Then do 18. Yeah.
hit the 1 on the X button.
Okay, if you do 1 over X, that button there. Okay, that gives you 1.6 times 10 to the minus 19. See the minus sign there? Again, that's how it reads. When you see a number here and a little number there, that means this number times 10 to the little number. So that's the times 10 is in between those. Now, some of the calculators actually show you a times 10 there, but most of them don't. So that's your fundamental charge. You cannot get a charge smaller than that. That's the smallest unit of charge you can get in nature. And by the way, they call that a quantum of charge. That differentiates y'all as auto mechanics from quantum mechanics. No, never mind. Okay. Done joke. Okay. So that's your fundamental unit of charge. I think we have time for, or it's a good time to do, example 6.1. Combing your hair on a dry day, those of you who have hair, okay, on a day with low humidity, results in the comb with a negative charge of, and by the way, your hair needs to be sort of clean too, because if it's oily, it probably won't work, results in a coulomb with a negative charge on the order of what? Ooh, this is in red. Let's get it to dark. Okay, I was reading it. There it is. 00 times 10 to the how many electrons? No, I'm sorry. To what charge? 10 to the minus 8 coulombs. And by the way, the unit is a capital C. I wonder why they use a capital C for the unit coulomb. Somebody's name. He was a French scientist. Seems like it was Charles Coulomb. I'm not absolutely certain on that, but it sounded a smart guy, you know. Okay, so I believe that was it. And guess what? A lot of your early scientists that did a lot of the groundwork for electricity were from France. I don't know why. This was the height of their system. Coulomb, Ampere, several of them were from. What's that? I can't hear you. Oh yeah, well yeah, and this was right before they had the French Revolution too, but so they were getting ready to fight. Yeah, and they did. They really did. And actually, who was an American, not just scientist, but statesman, politician, just a jack of all trades, inventor, who dealt with some with electricity? Benjamin Franklin. And guess where he was an ambassador one time? France. You know, when he was over there, he wasn't just doing politics. He probably got together with some of these Ampere and Coulomb. I think they were about the same time, and they probably did some pretty serious science discussions among themselves. So it was sort of a small world back then. Yeah, exactly. He knew that lightning was some form of electricity, and so he went out in an electrical storm flying a kite, and he was smart enough to attach the key to it so the charge, when it did get struck, would go down to the key rather than go down to him. And that's what saved his life, by the way. Huh? Yeah, exactly. And maybe that guy got cried. Okay, I don't know. Okay. Too bad I hadn't paid you. Never mind. Okay. So that's your charge, Coulomb. Okay? And what's the symbol that represents the charge? The parameter? Small q. Exactly. There's your small q. Okay? How many electrons? So we're looking for N, the number of electrons. How many electrons were transferred from your hair to the comb to produce a charge of 1 times 10 to the minus 8 coulombs? Okay, so your N would be, very good, Q over E. Okay, now, and using what we just talked about there, your Q here is 1.00 times 10 to the minus 8 coulombs, and your fundamental charge on your electron was 1.60 times 10 to the minus 19 coulombs per electron, right? That's what we found out. Yeah, coulombs per electron. Okay? So with your calculators, punch those numbers in and see what you get. Does everybody know how to find the EE or EXP key and to do the scientific notation? Because the general idea is don't do times 10. You know, there's a lot of number punching there. If you use that key, it gets you right there. Anyone got it yet? Okay, 6.2, it really should be 4, but they put it as 5 times 10 to the what exponent? Negative what? Negative 10. Yeah. That would be how many electrons. Okay, that would be, and I usually put an E by it because you see in math, E is the exponential function. It's actually a number. So I put a minus sign to tell myself that's not the number E, that's the thing. Now, oh, and it's not minus, it's plus. I was just going to say the book has it wrong. If you look at the book, they have 10 to the minus 10. No way. It's a lot of electrons. It's 6.25 times 10 to the 10th electrons. It really should be 6.24.
When I did it on the calculator, I came up with 10 to the 10, but I thought
No, it is.
it was wrong.
The book is wrong. Change that. If you got your book, it's 10 to the 10th. All right. Now, that they say is 62.5. That's 6.25 times 10 to the 10th is 62.5 billion electrons. Did you know you had done that much when you combed your hair? Okay. Let's move on to
So
the.
anybody could have been a scientist. Can't nobody refute what they say.
What's that?
So anybody back then could have been a scientist.
Yeah.
Because can't nobody refute what they say. I mean, it's like, I can make up something. Oh, that's amazing.
Well, I mean, you're what? Automotive. What's your major? Robotics. Okay. If you went far enough back in time, could anybody have been a robotics major? No, they didn't even have
A
them.
lot of that wasn't proven until years after they're dead. I mean, the
Right.
people that's around don't know.
Yeah, but they were still good scientists and technicians and engineers.
So I guess the word was people
Yeah.
back then that was just,
That were charlatans? Sure there were. I bet you today there's probably a few, aren't
the college name
Yeah.
of that person.
What
there?
about the guy that told everyone the world was flat?
Yeah,
And he's still a scientist. So.
and he was probably considered, yeah. Aristotle was greatest thinker of all time, and what, half of his stuff, more maybe, turned out being wrong. But guess what? This is a story. I don't know if it really was true. They said that, but it was sometime in my lifetime, so it's recent history, no matter what y'all may think. Hey,
This stuff
okay.
on us.
That the dean of the Harvard Medical School was speaking to his graduating class, and he said, you people out here are the best trained, you've had the most modern, up-to-date techniques, procedures, equipment. You're the top that's ever has been in this field. Okay? Two things wrong. Probably half of what we taught you is wrong, and we don't know which half. Okay? And that's probably true. Probably what we consider to be true today, absolutely, without a doubt, someday in the future we'll say, that wasn't quite true. They're off a little bit. They're not quite right. I mean, Newton came up with the law of gravitation, and it worked for centuries, and was perfectly fine until Einstein came along and said, but if you go to the microscopic level, that this is really how gravity works. And sure enough, it seems to be that is the case, that Newton's idea wasn't comprehensive enough.
But again, you could have told somebody the earth was round. How could they prove you any different?
What, that it was round or it wasn't?
That it was or wasn't. They couldn't prove one way or the other.
Well, yeah, you sort of can. If you've ever been out in the ocean, all by yourself at night, on a ship or something, okay, and another ship is coming toward you, what you first see is just a little speck of light. Before that, you saw nothing. But the closer you get, the taller that is. Why? Because the curvature of the earth it's curving away from.
So if you can do that on land, though. If
You
get
can
up
do it
high
on
enough.
land, yeah. Second?
I said you can do it on land if you got up high enough.
Yeah, exactly.
So I mean, it really is just how high up you are.
Exactly. And that's exactly it. Why do they put the forest station, out, fire watchers, put them way up in tower because they can see far further down the horizon than you can if you're down here. So obviously, the Earth has to be curving away from it. Okay.
People that thought, man, it's gonna fall off the Earth. They said this way.
We can figure all this stuff out, but they don't know how they built the pyramid.
No, we don't. Okay. Or how they did Stonehenge. You know what Stonehenge is? Yeah, the rocks. I mean, they're not little rocks. They're huge boulders. And they have them standing here and another one across the top. When they first were built, formed a perfect circle. Huge boulders. Perfect circle. And if you're in the middle, the certain galaxies come into the scene at regular intervals, rising through that. They had it down. Number one, and the rocks weren't from that area. They had them shipped in. How did they get them there? How did they get them set up? How did they get that kind of precision?
They were on hash.
Say again?
They were smoking hash.
What's what?
They was on hash.
No,
Oh.
that they had to be on cocaine.
It was, and it was such an ancient people. We don't even know who did it. So how in the world? Yeah, just like the pyramids. Yeah, how in the world did they do that?
Probably Flintstones did it.
Yeah. Okay. Yeah.
What's that thing that's like, it's like set up like there's a huge stone that's set up perfect way or whatever.
Right.
You just touch it at the door, and it's huge.
Yeah.
I can't remember what it's called. So it on
It's what?
It's like a huge door.
Right.
It's made out of like a huge rock, and they had to set it just a certain way where you can just push it with your hand.
Yeah. And where is this?
I don't know. I can't
Oh,
remember what it's called.
yeah. But you've seen it. Yeah. Okay. Yeah. It's pretty incredible. How did they do that? Okay. All right. So let's move on from electric charge to electrostatic forces. Now, we think we're going backwards, going back to static. We're really not. In fact, we haven't really left it yet. But let's look at this. And Coulomb, the same guy for whom the unit was named, he came up with this law. And this is the relationship, Coulomb's law, relationship giving the force between two charges. Okay? And here's what Coulomb's law is. F, that's the force, is equal to, this is your proportionality constant. So the way he first expressed it is the electrostatic force between two charges is proportional to the product of the charges and inversely proportional to the square of the distance between them. And the constant proportionality for both of those is this K. And this K is not just, doesn't depend on the charge, it doesn't depend on the distance. It is a characteristic constant of nature. And it's 9.00 times 10 to the 9th. And then what units? Well, for it to have newtons here, there has to be a newton here. Well, there's no newton there. So the newton has to be in the K. But this has divided by meter squared, so your constant must have a meter squared in the numerator. And this has the Coulomb squared up here, so your constant must have Coulomb squared in the denominator. So these can cancel those out. This can cancel the units out, not the numbers, but the units out, and that leaves you with newtons. So there's your unit. The proportionality constant is 9.00 times 10 to the 9th Newton meter squared per Coulomb squared. Okay?
So that's electrical force.
That is, yeah, electrostatic force. Exactly.
They use the same letters for different forces.
Oh, yeah. Yeah, K is used for just about tons of
I'm talking
things.
about the formula for force.
Yeah.
Like if you in hydraulics, it's area of time pressure. So
Okay, force is, pressure is force per unit area, yeah.
this could get confusing. You're reusing the same.
Yeah, but it's still a force. Still a force. Force is always given that capital F. It's, we call it what?
Yeah, electrostatic.
Well, no, a force doesn't matter what is creating the force. The force is measured in newtons, and this is a force. If you had this force was creating a pressure, that would be the same force that then is your pressure times area. Okay, so you would want that to have the same letter. Yeah, but a force. Yeah, you have several different things. Force is mass times acceleration. You know, there's another. Yeah, it's the same type thing, but this is your electrostatic force. Now, they want to compare that with Newton's law of gravitation. I don't know if y'all remember that one. That was only a couple chapters ago, so surely you remember, right? Here was Newton's law of gravitation. F there, I wish they had put the G down here. That's the product of the masses divided by the distance squared. So the distance squared was the same in both. Then that one up there, it was QQ, Q1, Q2. Here's M1, M2. But the G, your constant proportionality here, is 6.67 times 10 to the negative 11. And again, Newton, and now they missed this unit there. That unit should be meter squared. They messed that up. Per kilogram squared, okay? Because that would be your masses. So this is over kilogram squared or kilogram to the minus 2. But they left off this. I think in the book they got it right. If you can find it in the book. I don't see it, but it's... You'd have to go back to the previous chapter, okay? But that's what you got, okay? So if you compare that, now certainly masses in kilograms you can't compare to charges in Newton and coulombs because they're just different apples and oranges. And kilograms is a big amount of mass. A coulomb is not a huge amount of charge, but still, look at the difference in your proportionality constants. This is 10 to the negative 11. That one was 10 to the positive 9. You got 9 orders of magnitude there. That's not enough to let your coulombs and your kilograms, not created by that. Electrostatic force is much stronger than gravitational force. How do you know that? Remember when we're talking that comb and the pieces of paper? You hold the comb near the paper, and what does it do? The paper comes up. So it goes against gravity, so that electrostatic force is stronger than the gravitational force on that paper. So, yeah, that is significant. Okay, that constant is quite a bit more. So I think we're ready for example 2. And here's where they compare those. K divided by G, 9.00 times 10 to the 9th divided by 6.67 times 10 to the minus 11. Do that on your calculator, you're going to get that ratio is for 10 to the 20th. 20 orders of magnitude greater K than G. Pretty impressive. Okay. So let's do example 6.2. Electrons carry negative charges and revolve around the nucleus of the atom, which carries a positive electric charge of the proton, from the proton. The electron is held in orbit by the force of electrical attraction, typically at a distance of, so here's your distance, d, okay, and this distance here is approximately, I lost it, there it is, 1.00 times 10 to the negative 19, no, negative 10, I was on the wrong line, negative 10 meters. What's that? No. There's, we aren't far enough in the chapter. In fact, just to give you an idea, we're on page 144. Before we'll do the next lab, we've got to go probably to about 150. So we'll work some more on this, and in the first 2 hours of next time, we'll get far enough along to do the lab. So next time, on Tuesday, we'll have about 2 hours of class, continuing chapter 6. We'll have 2 hours of lab. That'll be the current lab, the circuit lab. And then we'll have, the last half hour, we'll have the test on chapter 4. Okay. So have a good weekend. All right. Okay. All right. Mass exodus, huh? Okay. Okay. So let's continue the problem. They're about 1 times 10 to the minus 10 meters apart. By the way, that distance there is pretty close to the unit they used to use. No one uses this much anymore. An angstrom. That's your atomic or molecular distances are usually in angstroms. No one uses that anymore. They use SI units. What is the force of electrical attraction between the electron and the proton? So, excuse me. Let me get that 2 out of there. Whoa, it didn't go, did it? It still didn't go. There it went. Okay. Now, so what's your formula for electrostatic force? F is equal to K Q1 Q2 over D squared. Okay? Now, your K was your electrostatic constant, or Coulomb's constant. That's 9.00 times 10 to the 9th Newton meter squared per Coulomb squared, times your Q1. Well, now this is talking about a single proton and a single electron. And if you go back 1 page, that's your 1.60 times 10 to the minus 19. 1.60 times 10 to the minus 19 coulombs times, again, a 1, because the protons and neutrons have the same charge, they're just opposite signs. 1.60 times 10 to the minus 19 coulombs. And divide that by your distance there, 1.00 times 10 to the minus 10 meters squared. Okay? Now, looks like a place for a calculator. I'm not going to do this one in my head. So, know how to use those scientific, the E or EXP buttons on your calculator. Or you can just put 9 EE or EXP 9 times 1.6 EE or EXP negative 19. Now, some calculators, the old scientific calculators, you would have to put the 19 first and then do a change sign key, plus minus key. Your newer calculators, you can put the minus sign that's in a parentheses. That's your negation key, and you do that before you enter 19. So it just depends on your calculator. You have to know your own calculator. If you're not certain, ask me and I'll try to figure it out. So you do times 1.6 EE or EXP negative 19, and then times another 1.6 EE or EXP negative 19, and then divide that by a 1 EE or EXP minus 10 squared. That last number, you square it. Second? Yeah, when you square it, it'll go to a minus 20. If you don't want to mess with squaring it, you just do divided by 1 EEXP minus 20. That's the easier way to go. Okay? And your meter squared cancels out the meter squared down here. The Coulomb squared cancels out those 2 coulombs. So you should get some number. What was that number?
I take it to 23.09. 23.04.
Yeah, 2.30, drop the 4, times 10 to the...
Mine take it 1 decimal place over, take it to 10 to the...
Okay, you've got it in engineering mode, don't you? every 3 digits. So you had 23? Or,
0.04.
yeah, okay. If you're in scientific notation, it would go to the -8. So 10 to the -8 newtons. Okay? Now that doesn't look like a lot of force, but you got to realize these are tiny, tiny, tiny little particles with very small masses, so the accelerations would turn out being extraordinarily large. Right? Yeah, scientific is that. Very good. And the reason we go with 3 digits, you had 3 digits here, you had 3 digits here, you had 3 digits there, you had 3 digits there, everywhere 3 digits, so that's why you don't use the 4. Okay. All right, good deal. Now,
I did mine different. I did the 1.6 times itself,
right,
and then I multiplied the 9 times 10 to the 9. And then whatever else I got, I divided it by the 1 times 10 to the -10.
okay,
I did the Q1 and Q2. I multiplied them together first.
right,
Whatever I got, I multiplied it times K, which is 9 e to the 9.
right,
And whatever else I got after all that, I divided by 1 times
10
1
to
e
the -20. I think you said you used -20.
Yeah,
didn't you?
-20.
Yeah, okay. All right, so that's electrostatic forces. Whoa, thought I was through. Okay, now we get to fields. Electrostatic, well, fields.
That's science fiction, right?
It's what?
Force field, that's science fiction, right?
No, not really. I mean, they use it a lot in science fiction, but fields are really there. How do forces act through space? Good question. Okay? How does the sun's gravity hold the Earth in place in orbit? There's 93 million miles between the Earth and the sun. It has to be a field. There's nothing connecting it. There's no strings, no strings attached. Nothing is there. Something has to be
The
active.
speed of the Earth, keeping it from speed of the Earth going around, keeping it from going.
Going into the sun, but the sun, if it weren't for the gravitational field of the sun, we'd be flying away from the sun. You know, there wouldn't be anything pulling us in. So the sun's pulling us in, but our speed's keeping us from crashing. So yeah, it's a nice equilibrium there, but what is doing it? There's nothing connecting us, and that's the field. The fields are what's doing it. Charges are surrounded with electric fields. Now, fields are vector quantities, meaning they have magnitudes and directions, okay? And the fields and the charges are inseparable, okay? If you've got a charge, you got a field.
You said vector, something like X, Y, and Z?
Yeah, like that, but like we were talking about before, a vector quantity, okay, my mass is just how much of me I am, okay? There's no direction associated with it. My weight is pulling me down toward the center of the Earth. So weight is a force, it's a vector quantity, mass is a scalar. It's just, as far as mass is concerned, I'm just a blob, okay, of how much of there is of it, okay? Speed is your magnitude of your velocity, but velocity has a direction associated with it. Vector just means it's got a magnitude and a direction, okay? So, if you got a field, you got to have a charge somewhere, an electric field. It has to be a charge somewhere. If you got a charge, it's guaranteed to be a field. Fields act on other charges. Now, electric fields act on other charges. You also have magnetic fields. You also have gravitational fields. So deal with those separately. But when we're talking about electric fields, they act on other charges. Now, the direction of the field, here's how you tell what it is. You imagine a small positive charge. So, let's say we have a charge out here. You tell me what kind of charge that is, positive or negative, I don't care. A positive charge, a positive charge here. Now, if there's a charge there, there's field all around it, all dimensions around it, okay? So let's say we have a little negative charge here. A little positive charge here. What is this charge going to feel from that? Yes, it's going to want to go exactly opposite from that charge, repel. So therefore, its field line would be pointed away from that positive charge. Okay? Whatever a small positive charge would detect, that's going to be the direction of the field. Now let's say that was a negative charge up here. Okay? And you have the same little positive charge here. What does it feel? Straight toward that. So the field from that charge would be in that direction. Negative charge, the field points toward it. Positive charge, the field points away from it. That's just the convention. Okay? And we visualize that with lines of force. Okay? They're not really there, but we use that to visualize it, sort of model it. The same ideas apply to gravity and magnetism. Now, there's one difference. Just like we've illustrated, electric field lines can point toward or away, okay, depending on the charge here. Magnetic field lines can point toward or away depending on what pole you have, the polarity. But gravitational field lines, always attractive, never repulsive, at least not in this universe, okay? They're always attractive. That's the only difference. These are always attractive. These can be either attractive or repulsive. Okay.
What would keep us on the Earth? The Earth is spinning and moving around the sun. What would keep us from flying opposite?
The gravitational field is so much stronger than what we would sense if we were fly off. Yeah.
I hear that, but I don't see how it makes sense.
Okay. Do you, were you following, I think it was a couple of summers ago, the European Space Agency sent up a probe to land on Ceres, or one of the meteorites, asteroids between Mars and Jupiter. They picked out one of the larger ones and they just wanted to land on it to see what it was like. Okay? And they did it. They actually succeeded in getting there and landing on it. Except when they landed on it, they bounced off of it because there just wasn't enough gravitational field there to hold them there. So the recoil was just enormous. So it had to change all of the calculations and come in really slowly, and even then they did. Well, because there just wasn't enough gravity. Well, we've got enough gravity. We land on the Earth and there ain't no getting away. There's no bounce at all, basically. So, same thing to keep us from flying off. Yeah, we're spinning, but nowhere hard enough to keep us from falling. And the other thing is that we're spinning with the Earth. So, yeah. We're in motion with the Earth, so there's no sense that we're getting flung off or anything. Yeah. We call that your reference frame is the same. So, yeah, there's no reason we would go off. Okay. So, here are the things. If your charge was a negative charge, the field line is always pointing toward you because small positive charge would be drawn toward you. But if your charge was a positive charge, the field line is always pointing away from you because small positive test charge would be repelled by. So the electric field lines point toward a negative charge and away from positive charges. Always. That's the convention for field lines. They're vector quantities, and that's what they follow. Okay? Okay. Now, there's a couple of things missing here because I keep hitting the button and it's not showing up. Here's what's happening if you picture the field lines, and still it's not a good picture. So let's say we have a positive charge here. Okay? Now the field lines are pointing away from positive charges. Remember from the last slide. Always pointing away from positive direction field. showed it. It was on there, I guess. Okay. Anyway, but it's going out in 3 dimensions. Okay, this is only showing 2 dimensions. Okay, you have another positive charge down here, not a test charge, but another positive charge. Its field lines are going like this. But guess what? They don't want to. And here's something about field lines. Field lines never cross, ever cross. So if these field lines are both pointing away, they're repelling each other. So now this is in 3 dimensions. You only see 2 dimensions here. So these fields, okay, if you sort of picture this small enough circle here, that's going in all dimensions. But you get away and they start bending away, and that's why the force is sort of like a spring. They're pushing them away from each other. Because these lines can't cross each other, ever. They can't ever cross each other, so they bend away from each other because they're pointing in the same direction. And this is what causes the repulsion. Now, if those were similar charges, like this, then the positive charge, the field lines are always pointing away, but the negative charge, they're always pointing toward, so this is pulling these toward it, you know. Now, again, I can't do this without blocking it, you know, if you put a circle around here, it looks like just an even distribution of charge here and here, but because these are being pulled toward that, the field lines do this, and this is what is attracting these two. So that's the convention of field lines. They're not really there, but the lines help us picture what's going on.
Like
Right?
2 magnets.
What's that?
Pretty much like 2 magnets.
Yes, exactly like 2 magnets. It's just ones are charges and ones are poles. Yeah, exactly like that. Except there is a difference there. You can have an isolated positive charge. You can have an isolated negative charge. You'll never have a North Pole without a South Pole. Ever, ever, ever. Or a South Pole without a North Pole. You'll never have a monopole. Doesn't exist, or we ain't never found one. You can't have individuals, so that's the only difference. What's that? Yeah, it may be in a few thousand years or 100 years or something. They may say, you know, they used to think you couldn't have these, you know, we don't know. Yeah. Okay. Now, the next topic here is electric potential. I think we can do this one, and when we finish this, we'll stop for the day. Electric potential. Forces are vectors. Electrostatic forces are vector quantities. Fields are vectors. Electric fields are vector quantities. But electric potential is not. It's a scalar quantity, only measured with a number. No direction associated with it. So it's a scalar field, but that's strange to call it a scalar field. Scalar means it has no direction. Field, you think it has a direction. It's not. It's a scalar quantity associated with a potential energy.
Is that misspelled? It would be scalar, right?
No, AR. Scalar is spelled with an AR. A scalar, ER, would be something that scales, like a fish scalar. You know, that would be an ER. This is a scalar quantity.
Every time you said that, I thought that's what word you used.
Okay. Oh, really? Okay. I should pronounce it better. Okay. All right.
When you said scalar quantity, I thought it was a quantity that you can measure. That's what I thought you was trying to explain.
No, it's a quantity that only has a magnitude with no direction associated with it. Yeah, only scales. Okay. Now, the unit for electric potential is your volt. Now, volt is a strange concept. Here's what makes it strange. The symbol for a volt, when you're doing an equation, like F equal ma, the symbol F means force, but it's measured in newtons. Okay? Okay. When you're talking about a volt, the symbol for volt is V, but the unit for volt is also V. So it has the same unit, like mass. The symbol for mass is M, the unit for mass is kilogram. Okay? What's that? Yeah, and in the old days we used E for electromotive force. E, yeah. Yeah, I bet they do. Okay? I knew when I was in they did. But nowadays, most books use V. And I don't like it. I wish we still used E. But you see, we use E for energy. And that gets confusing there, too. Okay? So they don't be using
We
V.
need a longer alphabet.
Yeah, exactly. Okay? Or maybe a capital epsilon or something like that. I don't know. Now, what is electric potential is related to the work involved in positioning charges. And work, remember, is a scalar quantity. No direction associated with work. Forces do have direction, work does not. Energy is a scalar quantity. No direction associated. So if it's related to work, it's a scalar quantity. No direction associated. So let's say, what you want this charge to be now? Positive charge here. Now, I have a little charge here, and you get to tell me, is it positive or negative? It's a negative charge. I want to bring this negative charge from here to there. How much work am I going to have to do?
Which charge is stronger?
Say again?
Which charge is stronger?
It doesn't really matter. That one's fixed. This one is mobile. So I'm going to move it from here to here. How much work do I have to do? It's going to be pulled by itself. In fact, the work I have to do is keep it from crashing into it. If I want to take it from there to there, I have to do negative work to keep it from crashing into that one, right? Second, yeah, I have to do work against it. So that is related to the work involved. But if this was a small positive charge that I was moving from here to here, I'm having to do positive work to force it to go there because it doesn't want to go, right? So with a negative charge, I'd be doing negative work. With a positive charge, I'd be doing positive work. So it's related to the positioning of charges. The potential difference is the important quantity. Not really what the potential is, but what's the difference between the 2 points. Important in producing forces and moving charges. Now, it's analogous to moving masses in a gravitational field. How much work do I have to do to move the book from here to here? Yeah, a positive amount of work. How much did I have to do to do that? Basically, negative work to keep it from keeping going. You know, I had to stop it there. So it's analogous to that. Okay? Moving masses in a gravitational field.
I've heard voltage described as if you have water in a pipe, it'd be the pressure.
Okay, very good. That's a pretty reasonable type thing. In fact, we're going to use the water pump analogy. It won't be today, it'll be Tuesday, but we'll get there. So here's sort of what I just did. That was a 1 Coulomb fixed positive charge that we had up there, and I'm taking a 1 Coulomb positive charge and moving it within, it doesn't say, let's say a meter of that one. How much work am I doing? That is the potential difference between these two. How much work did it take to move it from infinity to that position? Okay? And that would be positive work because it doesn't want to go there at all. Okay. Now, here is the formula for voltage. And this is a good formula to remember. What your voltage is, that's your potential difference, or electric potential. It's not Ohm's law. No, we're going to get to that later. We probably will get to it on Tuesday. Our lab will be Thursday on Ohm's law. What a voltage is the work done for every charge. Joules per Coulomb. That's what electric potential is. Related to the work, and how is it related? By the amount of charge you're moving. So the voltage or potential difference is work per unit charge. Okay? The work that it took to move the charge divided by the amount of charge, that's your potential difference. Now, we never measure these things anyway, but that's what potential difference is. So you really need to remember it's joules per Coulomb. Those are the units for voltage. Joules per Coulomb. Joules of work per Coulomb of charge. And we will be using that later too. Okay? We'll stop there and start with electric current next time. And the lab will be on electric current, or circuits anyway. And then after we do the circuit lab, the next lab will be the Ohm's Law lab. You want to do it today or wait till Tuesday?
Probably wait till Tuesday.
Tuesday, okay, great.
My brother's something else.
Oh, okay. I appreciate you hanging around and finish the class, though. Good deal.
See you next time.
All right. Have a good weekend. And I've got to go man the help desk for an hour and 15 minutes. And I bet you no students will come by.